Right. Good afternoon, everyone. Yes, Ankur Kashyap. Wait, where are you raising hands again and again? Right. So if there is any disturbance in your device, please check it. I'll give you a chance at the end for doubts. Please wait. Don't care, sir. What we are discussing? Don't care, sir. So what is the reason for getting don't care, sir? Just I started. Then why it is named as don't care also we mentioned. How to utilize don't cares we need to understand. So let me repeat once again. When we have n inputs, total number of input combinations possible is 2 power n. Out of 2 power n input combinations, there are some input combinations for which there is no possibility for occurrence. They never occur. That is the reason what should be the output for these input combinations is not specified. So then what should be the output? I don't care what system gives the output for these input combinations for which there is no possibility for occurrence because they never occur. What should be the output if it is asked? I don't care what system gives the output for these input combinations. But system functionality is expected input combinations, expected output. Expected input combinations, expected output. What about the input combinations for which there is no possibility for occurrence? For those combinations, output is not defined. Then what should be the output? I don't care. I don't care what system gives the output. Already I discussed example also. If I say that inputs is possible BCD means the possible input combinations is 00002 to 1001. And what about 1010 to 1111? They never occur because according to the specifications, inputs is natural BCD. The natural BCD means it must be occurring from 00002 to 1001 only. What about other combinations? According to my system functionality, inputs must be natural BCD only. Other combinations are invalid. Then don't apply those input combinations. Then what should be the output? If I'm applying these input combinations, I don't care. But then what is system functionality? Expected combination for 00002 1001. Whatever the output is specified, that should be given. What about remaining? I don't care. I don't care what system gives the output for remaining input combinations for which output is not specified. That is the reason these are named as a don't care. So I hope understanding two things. Why we are getting don't care? Function is incompletely specified. Function is incompletely specified. When function is incompletely specified, then for some input combinations, output is not specified. Those combinations we are considering as don't care. Why it is incompletely specified? There are some input combinations for which there is no possibility for occurrence at all. So concept is not don't care. Concept is a incompletely specified function. Right. Concept is a incompletely specified function. Then resulting don't care. Resulting don't care. So function is incompletely specified. That is the reason we are getting don't cares. Pratik Pramod, I don't have any answer for your questions because why you are not able to watch my video, I don't know. So I don't have any answer for your question, settings and all. I don't know. Please concern uh, technical persons or manager. because I don't have anything to set here. I don't have that solution also to give you. Please understand, Pratik Pramod, if you are not able to watch my video, if you are able to see screen as well as audio, if there is any issue with video, I'm not able to do anything with that. So if anything is there, would have told you when you are asked. I don't have anything. That is the reason I did not respond to your question. Please understand. If something I know, I always interested to express that. When I don't know, I'm not expressing. So if you are expecting any settings to watch my video, right? If you are expecting, I don't have that settings. If any problem is there, still if you are facing some such problems, please inquire with your friends. Some people might have rectified the problem. So otherwise, still if you are not rectifying the problem with your friends, please contact the managers or technical team. There may be supporting team. Please contact them. I hope you understood. I don't have answer for your question. That is settings to watch your video, right? Sir, I can't see you. Is there any settings in Chrome required to see you? Tell me, right? That's what you asked, right? Once again, you are saying that please tell me, right? So I don't have any information about that. That is the reason I did not respond to your question. I hope you understand. If anything I know, I'm always ready to express, right? So the concept is a incompletely specified function. Incompletely specified function. Reason for don't case is there are input combinations for which output is not specified. That is called incompletely specified function. Till now, what we have discussed, when minterms are given, all the remaining we have considered max terms. That is a completely specified function. The function so far we have discussed are completely specified function. For each and every combination, output is specified. Is it 0 or 1? Particularly it is specified. But when I say incompletely specified function, there are some input combinations for which output is not specified. Such combinations are called don't care. The reason to say don't care is the reason to say it is don't care is we are not caring what should be the output for that. After designing the system, intentionally if you are applying these input combinations, then what should be the output? I don't care. Because the environment where I'm using this system, there it is not possible to get these inputs. Even though it is applied intentionally, what should be the output? I don't care. I don't care. That's where we got a name, don't cares. Don't care is not concept. Don't care is result of a concept, incompletely specified function. So why it is incompletely specified, we have understood. Why these are called don't cares also we have understood. Now, last thing which is remaining is how to utilize don't cares, right? How to utilize don't care. The way it is helping us. Simple thing is the way it is helping us. What do you mean by this? For example, while minimizing in SOP, if don't cares are helping in reducing the complexity, then take the help of don't cares. Then we are considering don't cares as ones. But I'm not considering all the don't cares as ones. Whichever the don't cares are helping us in reducing the complexity, only those don't cares are considered as ones while minimizing in SOP. Remaining don't cares, we don't need to cover. And similarly, while minimizing in POS, what we are doing, whichever the don't cares are helping us in reducing the complexity, those don't cares are considered as zeros. What about remaining? We don't need to consider. Simple thing is how we utilize the don't cares is the way it is helping us in reducing the complexity. What do you mean by this? If don't cares are helping in reducing the complexity, take the help of don't cares. It may be either in SOP or POS. If don't cares are helping in reducing the complexity, then take help of don't cares. Else, don't care about don't cares. My statement is this. If don't cares are helping in reducing the complexity, then take help of don't cares. Else, don't care about don't care. What do you mean by this? Some don't cares may not be helping in reducing the complexity. Then we don't need to cover all the don't cares. Important thing is while minimizing in SOP, our aim is to cover all the min terms. While minimizing in POS, our aim is to cover all the max terms. Point should be understood correctly. While minimizing in SOP, our aim is to cover all the min terms. While minimizing in POS, our aim is to cover all the max terms. For that, don't cares may be helping, may not be helping. If don't cares are helping in reducing the complexity, then take help of don't cares. Else, don't care about don't cares. That's it. Simple thing. What is the meaning of this statement? Let us understand with the example. Whatever I mentioned, let me give you clarity with example. The clarity about the statements with example. Let us see what is exactly. Follow correctly. If you want to minimize this without taking help of don't cares, let me minimize this Boolean expression without taking help of don't cares. What I do first, without taking help of don't cares, I'm reducing. Then this is one grouping, second. I'm not taking help of don't cares. I'm trying to do minimal expression using only min terms. Then what we get here? A bar C plus BC. I hope you are following. A bar C plus BC, because I'm not taking help of don't. But if you're observing, if I take help of don't cares, there is a possibility for expanding the grouping. If you are taking help of don't cares, then it is possible to expand the grouping. Then resultant is C. If you are observing complexity of this and complexity of this is acceptable. Because don't care is helping in reducing the complexity. Don't care is helping in reducing the complexity. If I consider the don't care, yes, there is a possibility for expansion, there is a possibility for eliminating variables, then we are getting resultant is C. For the same, let me find minimal expression in POS. Minimal expression in POS. For the same, let us find minimal expression in POS. If I say don't care. Then, without taking help of don't care, if I do minimization grouping, what we get here? It is C. If I try to cover the don't care, then what happens, sir? This is another group. This grouping plus this group. Then what we get here? C and with A bar plus B. Then obviously complexity is increasing. Then we don't need to cover all the don't cares. Already all the maxims are covered. Already all the maxims are covered. What is this grouping? It is not covering any extra maxims. It is covering extra only don't cares. In such case, we don't need to consider this one. So we don't need to cover the don't care. Now understand the statement correctly. If don't cares are helping in reducing the complexity, then consider the don't cares. If don't cares are not helping in reducing the complexity, then don't care about such don't cares. Right? Here, don't care is not helping in reducing the complexity. Then I don't need to cover such don't cares. Whichever the don't cares are helping me in reducing the complexity, only those don't cares are to consider. Understand point correctly. Statement is what? If don't cares are helping in reducing the complexity, then take help of don't cares. Else, don't care about don't cares. Else, don't care about don't cares. Moving to next slide. Ms. Checker. Let me take some more examples to get more clarity about minimization in presence of don't cares. Find minimal expression in SOP as well as POS. Find minimal expression of this function in SOP and POS. First complete in SOP, later complete in POS also. Try when question is given, try on your own. Then let us see how can I group for SOP. This is one grouping and this is second grouping. Anything else is required? No. Already all the minterms are covered. Nothing is required to be covered. So then what is it here? A bar, B bar plus CD. A bar, B bar plus CD. Already all the minterms are covered. The remaining are don't gates only. We don't need to cover all the don't gates. Now let us find for the same function in POS. Right. Let me write maxims and don't gates. Find minimal expression in POS. Right. Very good. See, this is one grouping and this is second grouping. Any more groupings required? No. Any more groupings required? No. Then what is the expression here? This grouping is A bar plus C, and with the other grouping is A is changing B equals to 1, D equal to 0. B bar plus D. B bar plus D. Right? Moving to next slide. Same, find minimal expression in SOP as well as POS. Abhijit Arode. If it is required, I will discuss now. As it is not required, I'm not talking. Right? Right. So let us see what is it. This is a one grouping and this is a second grouping. Sufficient to cover all the midterms. Then what we get here? A C bar plus B bar D bar is a minimal expression in SOP. Similarly, minimal expression in POS. For the same, let us find minimal expression in POS. Then 0, 0, don't care. 0, 0, 0, 0, don't care, 0, don't care. Then find groupings. What is it here? This is one grouping, second grouping, and also third grouping. This grouping is resulting C bar. Vertically octave is resulting C bar. And what about this grouping in which CD are changing AB01? Then A plus B bar. AB01 means A plus B bar. Similarly, this quad is A equal to 0, D equals to 1, which is a A plus D bar, which is a A plus B bar. Manikanta, if you consider AB row in SOP, then one is corner grouping, plus again, this quad also should be considered. And what happens here? You are considering this one if you are saying, then what about this min term? Again, we need to consider this one. Complexity is increasing. Minimal expression. Don't forget that. Our aim is to cover all the min terms with minimum complexity. For that, don't cares are helping, take the help of don't cares. Else, don't care about don't cares. To cover the don't cares, don't increase the complexity. Manikanta, get the clarity. No. Ankur Kashyap, no. Yes. Yes, Manikanda. Very good. If you're understanding that, sufficient. For that only coaching is required. So we have our own assumptions. We do our own mistakes. We need to rectify that mistake. That's my duty to give you clarity. I'm doing that my level best. Yes. Find minimal expression in SOP as well as PYS. Vijay Durga Prasad. Perfect. Then let us see. This is a one grouping, corner grouping. To cover these two minterms, I can use either this or this. Two possibilities. Check it correct. Corner grouping is compulsory. To cover these two, I can use either this or this. Both are quads only. Complexity will be same. Then corner grouping is a B bar D bar plus here I can use C bar D or B bar D bar plus what can be that? B bar C bar. B bar C bar. B bar D bar plus B bar C bar or either this grouping vertically quad or this ends quad because these two minterms should be covered. We have two possibilities. So here also we are getting two minimal expressions. Shubham, preferable is without don't case. But with respect to complexity, both are same. Right? Preferable is without don't case. For the same, let us find POS minimal expression. Right. Don't care, don't care. 0, don't care. 0, 0. 0, don't care. 0, 0, 0. Now, let us group for minimal expression. This is one grouping octave. This is another grouping quad. Sufficient. So, in this grouping, what is it here? B bar and with C bar plus B bar. That's it. Tenth position 1 is covered. I don't know who is that, but someone is mentioning the 10th position is 1. It is not covered. It is covered. Pradeep Kumar Jana. Yes. Yugasri. Which one you are talking? If I consider this one, plus this one should be considered because if I consider this one, it is not covering all the minterms already. This is becoming compulsory, right? Corner grouping B bar D bar. Now to cover these two, which one is preferable? If I use this 1 1 XX or 1 1 don't care horizontally, if I consider what happens here, it is covering only one minterm. To cover this minterm again, either this grouping or this grouping should be considered. Understanding? Yugasri, complexity will be increasing. Yes. Pawan Kumar, I have been waiting for this question. Yugasri, I'll talk to you at the end. Please wait. Please wait. Yeah. Pawan Kumar. Gumbuluri Pawan Kumar. Yes, I've been waiting for this question. So now people might be thinking about SOP POIs are not giving same, or if you are ending these POIs terms, we are not getting SOP. That might be the question, right? But here expressions will not be equal. The reason is you are neglecting some don't cares. you are reusing some don't care, sir. That means don't care is considered as 1, don't care is considered as 0. How can you get expressions are equal? You won't get expressions are equal. Sometimes you may be getting equal, but not all the time, sir. So SOP, POS are not giving same expressions, but functionality is same. Then again doubting. What do you mean by functionality? Expected input combinations, expected output. Don't verify with don't care combinations. What is it here? Expect. Wherever it is 0 or 1 is specified for those combinations, if you are substituting in SOP, if you are substituting in POS expression, these two are giving same response. Expressions may not be same. Expressions may not be same. I'm not saying that will not be same. Expressions may not be same because what is happening here? If you are comparing these two, some don't cares are neglected in both, or some don't cares are used in both SOP as well as POS. That is the reason expressions may not be equal. Expressions may not be equal, but the functionality will be equal. What is functionality? Expected input combinations, expected output. Substitute combinations, then you will get a expected output. Both SOP and POS are giving same response with respect to expected input combinations, expected output. Just a minute, I'm changing. I am off. In POS, so we need to find a minimal expression in POS. Just use K-map. Then let me group. This is one grouping octave, second grouping which is octave. That is right resultant. This octave is resulting A equal to 0, B, C, D are changing. A equal to 0 means it is A. And this octave in which A, B are changing, D is changing. C equal to 0 is not changing. C equal to 0 means it is C. So as it is P voice, there must be flash, which is wrong. Which is wrong. So this is resulting A, this is resulting C. Right? We need to take product of these because we are writing sum term with respect to a grouping. The sum term is minimized to single variable. What can we do? So with respect to this grouping, there must be a sum term. The sum term is minimized to single variable. So again, this is one grouping. Here C is 0, which is not changing. So only one variable. Then we need to take product of these two. Product of sums. POS. So answer is B. Some of you are saying that C. Please check it. So you need to understand it is D. Yes. In this question, SOP is also same. So now you can say what is the conditions to get same SOP and POS expressions in presence of don't cares also. Here, yes, this is what EAC. In this, both SOP POS are giving same expression. When do we get SOP POS expressions also same? Even in presence of don't care, sir. Check about this, sir. I will discuss later. Or let me complete now itself. Why should be wait? Right. When comparing SOP POS groupings, when you are comparing SOP POS groupings, all the don't cares must be covered either in SOP or POS. All the don't cares must be covered either in SOP or POS. No don't care is used in both SOP and POS. Two conditions satisfied, then SOP POS expressions also equal. Functionally same. Expected input combinations, expected output. But expressions also to be equal. What is the condition is when you're observing don't cares, all the don't cares must be covered either in SOP or POS. No don't care is used in both SOP and POS. See, let me give you examples. In this case, if you are observing, these don't cares are used in both, or let me take a previous one. See, in this, if you are observing, this don't care is used in both SOP and POS. In such cases, it will not be equal. And in this, if you are observing, this don't care is not covered in both SOP and POS. So it must be covered either in SOP or POS. It should not be covered in both. And here, there is only one don't care that is covered in SOP. No don't cares are used in POS. Then these two will be equal. So all the don't cares must be covered either in SOP or POS, not in both. Not in both. If it is covered in both also, expression will not be equal. If it is neglected or if it is not covered in both also, expression will not be equal. So two conditions to be satisfied to get SOP POS expressions also equal is all the don't cares must be covered either in SOP or POS. No don't care is used in both SOP and POS. Right? In such cases, expressions also will be equal. Nagalingeshwar Rao. Right. Concept. So much is there in every concept if you are getting in depth. Right. So I'm expecting you to solve questions from K-map, Boolean, K-map. We have classroom practice questions. Try to solve all the questions. I will discuss. Right. Let me know your doubts in that questions. Right. Not immediately I'm solving. This concept is not required, but as people are asking, let me make it out. First condition is all the don't cares must be covered either in SOP or POS. No don't care should be covered in both SOP and POS. Someone was asking, what is that condition, sir? Yes, all the don't cares must be covered either in SOP or POS. No don't cares should be covered, right, in both SOP and POS. Moving to next slide. So I'm expecting you to solve all the questions from classroom practice questions, and if possible, try to solve all the questions from GATE and ESC papers. Right? Try to solve, try to get clarity. Very simple questions we have been getting, but silly mistakes we have been doing. We need to rectify all those mistakes before going to final exam. Right? So now, after completion of basics of digital circuits, now we are ready to design digital circuits. After completion of, right, basics of digital circuits, now we are ready to design digital circuits. Saidama, wait, I'll talk to you later. Digital circuits, we are ready to design digital circuits. We have two types of digital circuits. What is it here? Combinational, right, and sequential. In sequential, again we have, what is it? Synchronous and asynchronous. And asynchronous. Synchronous and asynchronous. Combinational and sequential, main classification. Again, sequential is classified synchronous and asynchronous. First of all, what is combinational circuit? Output depends on present input combination only. Output depends on present input combination only. It is combination of present inputs. So it is named as a combinational circuit. What is sequential circuit, sir? Output depends on present input and past output. So it is called sequential circuit. Once again, combinational circuit, output depends on present input combination only. It is combination of present inputs. So it is named as a combinational circuit. What about sequential? Output depends on present input and past output. Present input and past output. So may not be getting clarity what is this exactly, right? So present input and past output. But what about past output dependency? Past inputs, past to past output. Again, past to past output is depending on past to past inputs and past to past output. Finally, what is it here? Output is depending on order in which we are applying input combinations or sequence of input combinations. So why this is named as sequential circuits is output is depending on sequence of input combination. The order in which we are applying input combinations is deciding system output. So it is named as a sequential circuit. So it is named as a sequential circuit. Try to understand correctly. Output depends on sequence of input combinations. So it is named as a sequential circuit. So after getting into sequential circuits, we differentiate synchronous and asynchronous. Until that, please hold on. So after getting into sequential circuit, we differentiate synchronous and asynchronous. Until that, this combination and sequential difference you need to understand. What is combinational? Output depends on present input combination. What is sequential? Output depends on order of the input combinations or sequence of input combinations. Sequence of input combinations. Now, we are ready to design combinational circuits. We have a procedure for combinational circuit design. If there is no past output, that is the start of the system. System reset condition. Shanmukh. That is called system reset condition. From there, we are observing what is the sequence we are applying. Shanmukh. Right. Now, you will understand all those after getting into sequential circuit. Please hold on. Now, combinational circuit. What we said here, output is depending on present input combination. For each and every combination, depending on functionality, it may be resulting output 0 or 1. So, how to design this combinational circuit is let me give you steps. Decide number of inputs and outputs required to design the system. First step is what? Deciding how many inputs required and how many outputs required to design the system in the first step. Second step is deciding outputs 0 or 1 or what is the next one? Don't care. Decide outputs 0 or 1 or don't care for all the input combinations. Depending on functionality. How can I decide output is 0 or 1? Depending on defined functionality. Defined functionality. Then third step is find minimal expressions. Minimal expressions of outputs in terms of input variables. In terms of input variables. Fourth one is what is the last step after getting expressions? Design using logic gates. That's what we are doing. So first step is what? How many inputs required, how many outputs required. Second step is what? Deciding outputs 0 or 1 or don't care for each and every possible input combinations. Then finding minimal expression. Then designing using logic gates. This is what we have a procedure. So with examples, we understand all this procedure under that. Hold on. So here, this is a procedure to design combinational circuit. First step is what? Inputs and outputs should be decided. Then second step is deciding output, 0 or 1 or don't care. Then finding minimal expressions. Then using logic gates, we are completing implementation. Complete the implementation, right? So let us start with the combination. Now let us start with the adders. In that adders, what we can have? 1-bit adder. Next one is n-bit adder. What we are going to discuss, I am addressing. In 1-bit adder, once again, what we can have? Half adder, full adder. Right? What do you mean by half adder? What do you mean by half adder? So adders, in that we can have 1-bit adder and n-bit adder. Let us complete with the 1-bit adder, then we get into n-bit adder. So in 1-bit adder, again you are saying that half adder and full adder. What do you mean by this? So adding 2 inputs of 1 bit without considering input carry is half adder. If you are considering input carry also, then it is full adder. Try to understand difference correctly. In 1-bit adder, what is it here? Adding 2 inputs of 1 bit without considering input carry is half adder. If you are considering input carry, it is full adder. Full adder. So let us see one by one. First, 1-bit adder. After completion of 1-bit adder, we go for n-bit adder. In that, what we said first, half adder and full adder. Let us start with half adder. In 1-bit adder, we can have half adder as well as full adder. What is half adder? Adding 2 inputs of 1 bit without considering input carry. That means how many inputs required to add? We use 2 inputs A and B. Then what can be the outputs? When you're adding 2 inputs of 1 bit, the possible outputs can be sum and also carry out. You are not considering input carry, but the addition may be producing output carry. That is the reason we need 2 outputs. One is sum, other one is carry out. Other one is carry out. Point should be understood correctly. Half adder means adding 2 inputs of 1 bit without considering input carry. But this addition may be producing output carry, that is C out. So that is first step is completed. What is that here? Number of inputs is 2, number of outputs is also 2. Then let us write all possible combinations of inputs 0, 0, 0, 1, 1, 0, 1, 1. Then what should I do? Specifying outputs for each and every possible combination depending on functionality. What is functionality? Addition. So 0 plus 0, sum is 0, carry is 0. Any doubt in that? No doubt in that. 0 plus 1, no doubt, sum is 1, carry out is 0. 1 plus 0, sum is 1, carry out is 0. 1 plus 1. What is 1 plus 1? 2. 2 in binary is 1, 0. 1 is carry, 0 is sum. Once again, 1 plus 1 is 2. 1 plus 1 is 2. 2 is nothing but 1, 0. 1 is carry, 0 is sum. That's what I have written. 1 is carry, 0 is sum. Now, let us find Boolean expressions for outputs in terms of input variables. So, what is it? Yes, here it is 1, here it is 1. Which combination of A, B? 0, 1 and 1, 0. Input combinations of 0, 1 and 1, 0. For these, some output is 1. So, A bar B plus A B bar, which is A XOR B. A XOR B. What about carry out? Carry out is 1 only when AB is 1, 1, which is a and B, which is a and B. For AB 1, 1 only, carry out is 1. For AB 0, 1 and 1, 0, output is 1, which is sum is 1. So A bar B plus AB bar, which is A XOR B. Third step is completed. What is it? Finding expression for outputs in terms of input variables. What is the last step? Drawing. A, B, here it is sum, here it is carry. Sum is A XOR B, carry out is A and B. That is a off adder. Simple thing. Off adder requires two inputs, two outputs. Why two inputs? For adding two inputs without considering input carry means there must be two inputs. What about outputs? When you're adding these two, one is sum, other one is carry out. You are not considering input carry, but it is producing output carry. In the addition of two bits, yes, it is producing output carry. To hold that output carry, we need carry out another output, sum and carry out. For each and every possible combination, we are specifying outputs depending on functionality. What is functionality? Addition. After writing that outputs, now finding output expressions in terms of input variables. If you are observing S equals to 1 for AB 0, 1 and 1, 0. That's what I have written. A bar B plus AB bar. That is A XOR B. So carry out, if you are observing, carry out is 1 only when AB is 1, 1, which is a and B. Which is a and B. Moving to next slide. In one bit adder, next is what? A full adder. What do you mean by full adder? Adding two inputs, considering input carry also. Adding two inputs of one bit, considering input carry also. That means the input side we have AB and also another input which is input carry. So number of inputs required is 3 now. How many outputs? No doubt. Sum and carry out. Sum and carry out. When you're adding these three, it is producing sum and carry out. Once again, full adder is nothing but adding two inputs, considering input carry also. That is the reason A, B, C, I are inputs, sum and carry out are outputs. Now A, B, C, I possibilities 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. These are all possible combinations of ABCI. Now let us specify outputs, sum and carry out depending on functionality. What is functionality now? A plus B plus CI. So 0 plus 0 plus 0, sum is 0, carry out is 0. 0 plus 0 plus 1, sum is 1, carry out is 0. Any questions? 0 plus 0 plus 1, sum is 1, carry out is 0. Next, 0 plus 1 plus 0. Then again, sum is 1, carry out is 0. 0 plus 1 plus 1. 0 plus 1 plus 1. 0 plus 1 plus 1 is what? 2. 2 is nothing but 1, 0. 1 is carry, 0 is sum. And 1 plus 0 plus 0. Sum is 1, carry out is 0. Correct? Now 1 plus 0 plus 1. It is again 2. 2 is nothing but 1, 0. Sum is 0, carry out is 1. And again 1 plus 1 plus 0. Again 1 plus 1 plus 0, again 2. 2 is nothing but sum is 0, carry out is 1. 1 plus 1 plus 1. 1 plus 1 plus 1 is what? 3. 3 is nothing but 1, 1. Carry is 1, sum is 1. One plus 1 plus 1, it is 3. 3 is nothing but 1, 1. 1 is carry, sum is 1. Now, let me give input combination numbers to use K-map to find minimal expressions of sum and carry out. What can be that? 0, 1, 2, 3, 4, 5, 6, 7. Input combination numbers. Now, what is sum? S is equals to sigma m of what we have here? 1, 2, 4, 7. 1, 2, 4, 7. What about carry out? Sigma m of 3, 5, 6, 7. Input combination we need to observe. Carry out is 1 for sigma m of 3, 5, 6, 7. 3, 5, 6, 7. Then use 3 variable K maps. One, I'm analyzing for sum. 1, 2, 4, 7. No possibility for minimization. Clearly, if you are observing 0, 0, 1, one input is 1, 0, 1, 0, one input is 1, 1, 0, 0, one input is 1, 1, 1, 1. 3 inputs are ones. One input is one or three inputs are ones. What is this here? 3 input XOR. So sum is equals to A XOR B XOR C. A XOR B XOR C. Observe correctly. CI. We see CI. So what is it here? A XOR B XOR CI. Why? Here output is 1. When one input is 1, one input is 1, one input is 1, three inputs are ones. Then again another. So here we need to find expression for carry out. What we have here? Sigma m of 3, 5, 6, 7. What is simplification? This is one grouping, this is second grouping, this is third grouping. Then carry out is equals to AB plus BCI plus ACI. AB plus BCI plus ACI. Write the expressions. Then logic circuit can be XOR OR gate. This is sum. AB plus BCI plus ACI. AB plus BCI plus ACI. Check it out whether I have done correctly or not. Yes, AB plus BCI plus ACI. That is a full adder implementation. Functionality and how it can be implemented, full adder. Now, moving to next slide. Implement full adder using off adders and required logic gates. Implement full adder using off adders and required logic gates. Yes, Chakrabarti, correct. You will understand, Sajjan Singh. You will understand. Wait. When we are analyzing n-bit adder, there you will understand what is it? Input carry, not internal carry. It is input carry. Sajjan Singh. So we need to implement full adder using off adders and required logic gates Yes. So one off adder is accepting two inputs. If I say A and B are inputs, which is producing two outputs. One is A XOR B, other one is what? AB, correct? Off adder. Off adder which we have implemented. I'm using this. One off adder is accepting two inputs. Outputs can be one is A XOR B, other one is A and B. That's what I have used here. But what is required for full adder? A XOR B XOR CI. Then I can use another off adder. Another off adder. With one input is A XOR B, other input is CI. Then what we have here? XOR of these two, which is nothing but A XOR B XORing with CI. A XOR B XORing with Ci. Because A XOR B again XORing with Ci is becoming A XOR B XOR Ci. It is sum. What is second output of this off adder? A XOR B and with Ci. Why? And of these two. One is A XOR B, other one is Ci. So and of these two, A XOR B and with the Ci. Now, what is that full adder carry out? Sum is implemented, but carry out is remaining. That is right. Carry out expression. Carry out is equals to sigma m of 3, 5, 6, 7. Check it correctly. Sigma m of 3, 5, 6, 7. I'm writing the same once again. So carry out is equal to sigma m of 3, 5, 6, 7. Then what is that here? 3 A bar BCI plus A B bar CI plus A B CI bar plus A B CI. Correct? Check it correctly. 0, 1, 1, 3, 1, 0, 1, 5, 1, 1, 0, 6, 1, 1, 1 is 7. Now, if I take CI common, A bar B plus A B bar and with CI. If I take AB common in these two, CI bar plus CI, am I right? CI bar plus CI. Then what is this? It is A XOR B and with CI plus AB and with one is AB. Yes, these two terms are there. One is AB, other one is A XOR B CI. Take R of these two to get carry out. Here it is. Check it correctly. Sigma m of 3, 5, 6, 7, if you are expressing this, we are getting these two terms because these two terms are there. With these two, if you are expressing R of these two, because A XOR B CI plus AB is the expression, which is a carry out expression. Yes. Final conclusion is what? Full adder can be implemented using two off adders and one two input OR gate. Full adder can be implemented using two off adders and one two input OR gate. One two input OR gate. Once again, full adder can be implemented using two off adders and one two input OR gate. And what about off adder? Already we know that off adder circuit is one is XOR gate and gate. Let me replace that. Each off adder is replaced with XOR and AND gate. Then again off adder with two input XOR and AND gate. One is A XOR B, other one is what? CI. Then here it is A, B, CI. Here it is sum. What is remaining? OR gate. After completion of two off adders, one OR gate. Here we are getting carry out. Check it correctly. This is a full adder implementation using only two input gates. Here off adder, and two input OR gate. Off adder replaced with the two input XOR and two input AND gate. Two input XOR and two input AND gate and two input OR gate. Yes. Full adder can be implemented using two off adders and two input OR gate. Off adder replaced with two input XOR and two input AND gate. Two input XOR and two input AND gate. Right. If you have done with this, moving to next slide. Question is full adder is implemented using two off adders and two input OR gate. Half adder is implemented using two input XOR and two input AND gate. The propagation delays of XOR, comma, and OR gates respectively 2 nanoseconds, 1.5 nanoseconds, and 1 nanoseconds. The propagation delay of full adder is dash nanoseconds. Read the question correctly. Try to solve this on your own. Everyone should try. Yes. Manikanta, Nagasai Manikanta. Wait, you will understand. I think Manikanta is different, Nagasai Manikanta is different. Am I right? Yeah. Ankur Kashyap, wait. Yes. Read the question. Very good. Most of you are answering correctly. Right. See, according to the given specifications, of adder using 2 input XOR, 2 input AND gate. One more of adder with 2 input XOR, 2 input AND gate. Then again OR gate. I hope this is a complete circuit for full adder according to the specifications. Now in this, I need to estimate time required to stabilize the outputs from the point inputs applied. Let me say at 0 time we are applying all the inputs. Everyone should focus. Some of you have done a mistake. Please check your analysis. You have to change your way of analysis. Some did not respond also, or many did not respond also. For the I'm discussing, follow correctly. Yes. Why I have used this circuit is according to the specification. What is it here? Full adder is implemented using 2 off adders and 2 input OR gate. Off adder is implemented using 2 input XOR and 2 input AND gate. This is the final circuit of full adder. Now, assuming all the inputs are applied at 0 time, let us see what is the time required to stabilize the outputs of this full adder. So, if you are applying AB changes at 0 time, if there is a change in the output of XOR gate, it takes how much time? 2 nanoseconds. In worst case, it may be changing, it is taking 2 nanoseconds. Am I right? Now, AND gate. At what time inputs are ready? All these ABC are applied at 0 time. So, if AB is applied at 0 time, if it is changing, it takes 1.5 nanoseconds. Am I right? Anyone has any doubts? Because XOR gate delay is 2 nanoseconds, AND gate delay is 1.5 nanoseconds. Now, in this case, whether it is changing or not changing, we don't need to observe because it is not specified what is the input changes. Then, if it is changing, in worst case, how much time it takes? That's what we need to consider. So, what we are observing here, when inputs are applied or specific changes are applied, we observe whether output is changing or not. If it is changing, add propagation. If it is not changing, we don't need to add propagation. When input changes are provided, but input changes are not provided. When input changes are not provided, worst case conditions we consider, it may be changing. If it is changing, how much time it takes to stabilize here? Yes, if XOR gate output is changing, it takes 2 nanoseconds to stabilize from the point inputs applied. Coming to AND gate, AB changes are applied at 0 time. If AND gate output is also changing, it takes 1.5 nanoseconds to stabilize here. Coming to this XOR gate now. Coming to this XOR gate, analyze, observe correctly. One input is available at 0 time. This XOR gate, one input is available at 0 time. Second input is stabilizing in 2 nanoseconds. Then the time required to stabilize inputs of XOR gate is 2 nanoseconds. Then onwards, if XOR gate output is changing, it takes 2 more nanoseconds. So observe correctly what is it here. The time required to stabilize inputs is one is ready at 0 time, other is ready at 2 nanoseconds. Both are ready by 2 nanoseconds. If these changes on inputs, if there is a change in the output, it takes 2 more nanoseconds, means some will be ready in 4 nanoseconds. What is it here? Time required to stabilize all the inputs of gate, then propagation delay of this should be added to this. Then we are getting time required to stabilize the output. When you are observing a logic gate or logic circuit, what is the time required to stabilize the input? Then add delay of this logic gate or logic circuit to get time required to stabilize the output. Yes, this XOR gate, one input is ready at 0 time, other input is ready by 2 nanoseconds. Both the inputs are ready by 2 nanoseconds. Then onwards, it takes 2 more nanoseconds to stabilize the output. So it takes 4 nanoseconds to stabilize the output. Coming to this AND gate, what is it here? One input is ready at 0 time, other input is ready at 2 nanoseconds. Both the inputs are ready by what time? 2 nanoseconds. Then onwards, if AND gate output is changing, it takes 1.5 nanoseconds more. That means it is 3.5 nanoseconds. Once again, for this AND gate, one input is ready at 2 nanoseconds, other input is ready at 0 time. Both the inputs are ready by 2 nanoseconds. Then onwards, if AND gate output is changing, it takes 1.5 nanoseconds. That is 3.5 nanoseconds. Coming to OR gate. One input is ready by 1.5 nanosecond, other input is ready by 3.5 nanosecond. Both are ready by. Don't say that 3.5 plus 1.5. No. So this is ready by 1.5 nanosecond. This is ready by 3.5 nanosecond. Both are ready by 3.5 nanoseconds. It is not one after the another. Observe correctly. This is ready in 1.5. This is ready in 3.5. Both are ready by 3.5. That's it. So after changes have occurred here by 3.5 nanosecond, if there is a change in the output, that change is occurring in 1 more nanoseconds. That means 4.5 nanoseconds. 4.5 nanoseconds. Check it correctly. 4.5 nanoseconds. That means from the point inputs applied, the time required to stabilize all the outputs. One is ready by 4 nanosecond, other is ready by 4.5 nanosecond. So to stabilize both, it is a 4.5 nanoseconds. 4.5 nanoseconds. One is ready by 4 nanosecond, second is ready by 4.5 nanoseconds. Both are ready by 4.5 nanoseconds. So assuming all the input changes are applied at 0 time, each and every gate delay is propagated by adding worst case delays. Then we are observing what is the time required to stabilize all the outputs. Sum is ready by 4 nanosecond, but carry is ready by 4.5 nanosecond. Both are ready by 4.5. 4.5. So once again I'm explaining, check it correctly. Right, some of you may be having confusion, sir. Some of you may be doing this type of analysis first time because already they have given question. This is a previous gate question. Right, let us see how to analyze. At 0 time, all the inputs are stabilized or all the inputs are applied. Now, we know each and every gate delay. So, let us see what is the way we analyze it to stabilize the outputs, how much time it takes. Yes, XOR gate inputs are ready at what time? 0 time. If XOR gate output is changing, how much time it is taking? 2 nanoseconds. AND gate inputs are ready at what time? 0 time. AND gate output is changing. It takes how much time? 1.5 nanosecond. If AND gate output is changing, it takes 1.5 nanosecond. Coming to this XOR gate, one input is ready at 0 time, other input is ready by 2 nanoseconds. How much time it takes to stabilize all the inputs of this XOR gate? 2 nanoseconds. Then onwards, it takes 2 more nanoseconds to stabilize the output. That means it is 4 nanoseconds. Coming to this AND gate, one is ready by 2 nanoseconds, other is ready by 0 time. Both are ready by 2 nanoseconds. Then onwards, if AND gate output is changing, it takes 1.5 nanoseconds. 2 plus 1.5 is 3.5 nanoseconds. Coming to OR gate, one input is ready at 1.5 nanosecond, second input is ready by 3.5 nanosecond. Both the inputs are ready by 3.5 nanoseconds. Then onwards, if OR gate output is changing, it takes 1 more nanosecond, means 3.5 plus 1, it is 4.5 nanoseconds. Sum is ready by 4 nanosecond, carry is ready by 4.5 nanosecond. Both are ready by 4.5 nanoseconds. 4.5 nanoseconds. If anyone is having any doubts, please type in the chat box. Yes. Yes, to that's true. Neeraj Meshram have been explaining 4.5. So second time also explained. Sahil Singh. What is 4 and 4.5? Sahil Singh. What do you mean by that 4 and 4.5? I need to explain. Here we are getting 4, here we are getting 4.5. So sum is ready by 4 nanosecond, carry out is ready by 4.5 nanosecond. Both will be ready by what time? 4.5. If I'm waiting for 4.5, it is ready by 4 itself. But for this, I have to wait for 4.5 nanosecond. By 4.5 nanosecond, both will be ready. Yes, Om Shri Krishna. Sridhar, yes. Sridhar, this is ready by 3.5, this is ready by 1.5. This is ready by 3.5, this is ready by 1.5. These two are ready by how much time? 3.5 only. Otherwise, if you are expecting that, why can't you take 3.5 plus 1.5 means, here I have to take 4 plus 4.5 is 9 or 8.5. No, simply what is it here? This is ready by 3.5 nanosecond. This is ready by 1.5 nanosecond. Both are ready by 3.5. So whichever the latest input is dominating, time required to stabilize the inputs when you are considering, don't add that time required to stabilize individual inputs. No, this is ready by 1.5, this is ready by 3.5. This is ready by 1.5 itself. All the inputs are ready by 3.5 because this is getting ready a bit late compared to this. This is already ready by 1.5. This is taking 3.5 nanoseconds. Both are ready by 3.5 only. Don't take addition. Sridhar, thank you. Thank you. Thank you. Propagation delay of full adder is now 4.5 nanoseconds. Naveen. One nanosecond we have added to. See, time required to stabilize the inputs of this OR gate is how much? 3.5. Then OR gate delay is how much? 1. 3.5 plus 1, it is 4.5. Please understand. Time required to stabilize all the inputs of OR gate is 3.5. And OR gate delay is how much? 1 nanosecond. That is the reason it is becoming 4.5 nanoseconds. Any more doubts? Very good. Yugashri. Understood? 1 nanosecond of OR gate delay is added to OR gate inputs are stable in 3.5 nanosecond. OR gate delay is how much? 1. So 3.5 plus 1 is 4.5. Yes. Very good. Very good. Right. Yes. Manikanta Choni, there is nothing but a critical path or maximum time required to stabilize the outputs because the input changes are not provided. That is the reason I don't know whether a gate output is changing or not. As input changes, for example, ABR, ABCIR 001, now it is becoming 110, then what will be the propagation delay? Then we can consider wherever there is a change in the output, there only we consider propagation delay. But here, input changes are not provided. When input changes are not provided, assuming each and every gate output is changing, we are calculating propagation delay. Manikanta. Yes, this we have considered, right? Sagarika, we have considered at input of OR gate, this is ready by 1.5, this is ready by 3.5. Both the inputs are ready by 3.5. OR gate delay is 1 nanosecond. Yes, 3.5 plus 1 is 4.5. Please, when I'm explaining, follow my words correctly. Yes, we should not add. When you are analyzing time required to stabilize the input, one input is taking that X time, another input is taking Y time. Whichever is greater, that is the time required to stabilize all the inputs. Don't say that X plus Y is the time required to stabilize. Satvik. AND gate delay is 1.5. AND gate delay is 1.5. Why do you want to take 2 nanoseconds? Venkana, check it correctly. What is the delays provided for each and every? Sagarika, why do you want to add 3.5 plus 1.5? That's what I've been mentioning. When you are up again and again, I'm mentioning what is it here? Don't add time required to stabilize the inputs. This is ready by 1.5. This is ready by 3.5. Both are ready by 3.5. Why do you want to add here at input side? What is the time required to stabilize the inputs? This is ready by 1.5. This is ready by 3.5. Both are ready by 3.5. Then R gate delay is how much? 1 nanosecond. See, a logic circuit. For example, we have two inputs. Input 1, input 2. This input 1 is ready in X time. Input 2 is ready in Y time. Right? Right. Now, what is the time required to stabilize the inputs? Maximum of X comma Y. Check it correctly. What is the time required to stabilize the inputs is maximum of X comma Y. What is the time required to stabilize the F? If the Z is a logic gate delay or logic circuit delay, then what is that F? Maximum of X comma Y plus Z. Simple thing. What is that? Logic circuit delay. What is the maximum of X comma Y? Time required to stabilize the input. That's it. Simple equation we can use. When you are analyzing worst case propagation delays, you can go with this. Time required for input is X. Time required to stabilize another input is Y. Then what is the time required to stabilize the inputs? Maximum of X comma Y. If the propagation delay of this logic circuit is Z, what is the time required to stabilize the output? F is maximum of X comma Y. Time required to stabilize the input plus propagation delay of this logic. That's it. Simple way. If still anyone is having any doubt, let me know. I'm there to help you. Yes, Sharanya, please, because as we are in this topic, some people are trying first time. Instead of going to next topic immediately, some people may be lagging in all the topics. They may be feeling that, oh, digital. That is the reason, whenever it is required, I'm addressing students' doubts. Please wait. Right. So we have to. Please understand my words in a positive way. अरे यार परम पूरा समझ में आएगा. You will understand later. Hold on. Param. If all the inputs are ready at 1 nanosecond, means time required to stabilize the inputs is 1 nanosecond only. Maximum of 1 nanosecond, 1 nanosecond is 1 nanosecond only. Anand, where are you getting such doubts? Even when I have given equation, so why are you getting doubt? If two inputs are there, two inputs are ready in 1 nanosecond itself. What is the time required to stabilize all the inputs? 1 nanoseconds only. Because maximum of 1 nanosecond, 1 nanosecond is 1 nanosecond only. Yeah, Akash, wait. All such questions are waiting for you. When input changes are provided, how to analyze propagation delay. I will discuss. Leave it to me. I will help you in that. Such questions also given in GATE 2017 EC. And propagation. I already mentioned propagation delay is not a very simple concept which you are expecting. It is there everywhere in our digital circuits. We have to understand in depth. Correct? Hold on. Yugashri, if you are adding to 1.51, we are getting 4.5, right? So why can't we do that addition you are saying? For that, I have a uh, simple slogan or simple thing which I know. Three cancelled, six cancelled, nine cancelled. There is a reason 1/2. Is this correct, Yugashri? Is this way correct? Yes, answer is correct. But for getting this 1/2, are we doing this? Can we say this is also correct for this? This method is correct. Can we say that? No. Please, when I'm explaining concept, follow concepts correctly. I've been mentioning what is the time required to stabilize the input, what is the time required to stabilize the output. And I've given this equations also. Then again, if you're asking, if I'm adding all those delays, that means if I have one more level is there, then how do you analyze? Right? So we should not add the delays. So you are matching with the answer by adding these. That means you are not accepting what I've been explaining. Then I cannot help you. Please follow the concepts correctly. Here, answer is correct. Is that method correct? If I give another example, can I do in this way? No. That is the reason how we can get this 1/2. We know this. That's what I've been explaining. So let me explain the concept. Don't expect shortcuts to match the answers, please. So don't make it simple to match the answers. In this, a slogan or statement is there. Just because the outcome is right does not imply your method is correct too. Let me repeat that. Just because the outcome is right does not imply your method is correct too. Right? So answer is matching. If I have some other levels, next stage is there, then how do you analyze? So understand the concept. I'm there to help you. So don't make it simple to match the answers. So don't find your own shortcuts, please. Yes, I will discuss. Be Desai, I will do. Yes. Okay. If you have understood what we have done in this, I hope no one is having any doubt. Simple equation also I have given. Go with that. What is the time required to stabilize the inputs? Then add propagation delay. How to calculate time required to stabilize the input? Each and every input it is propagated. Then we are mentioning what is the time required to stabilize there. So if you are having that x and y are time required to stabilize the inputs of a gate, then maximum of x comma y is time required to stabilize the input. Then add propagation delay. Right. So now let me say that one bit subtractor let me consider. Then we get into comparator, then we get into n-bit adder. N-bit adder is not a simple concept. That is different adders are there. We need to consider different adders. So let me consider first one bit subtractor. One bit subtractor. One bit subtractor. In that again, off subtractor, full subtractor, right? half subtractor as well as full subtractor. First, let me consider half subtractor. Let me consider half subtractor. What is half subtractor? Let me say that A minus B is the operation. We are not considering input borrow. We are not considering input borrow. We are considering only A and B. Operation is A minus B. What can be the output? One is difference. Other one is borrow out. What is that borrow out? You will understand soon. Hold on. So what is it here? Operation is A minus B. We need to perform A minus B. And operation is A minus B. And outputs are difference and borrow out. So if A and B are inputs, what is the possibilities? 0, 0, 0, 1, 1, 0, 1, 1. 0, 0, 0, 1, 1, 0, 1, 1. Now, operation is what? A minus B. Let us see outputs. 0 minus 0. Difference is 0. Borrow is not required. Correct? For A minus B, 0 minus 0. Difference is 0. Is there any requirement of borrow? No. That is called output borrow. 0 minus 1. Listen carefully. 0 minus 1 cannot be subtracted. For that, borrow is required. Borrow is required. If you are taking borrow, it becomes now 0 plus base value. 0 plus 2, it is 2. 2 minus 1, difference is 1. Understand correctly? In decimal, when you are taking borrow, 10 will be added. In octal, when you are taking borrow, 8 will be added. In binary, when you are taking borrow, it becomes 2 will be added. So 0 is there. 0 minus 1 cannot be subtracted. If you are taking borrow from next position, 0 plus base value is 2. 2 minus 1, difference is 1. Very simple. So the existing add base value. 0 is there, adding base value. What is base value? 2. 0 plus 2 is 2. 2 minus 1, difference is 1. Now 1 minus 0, difference is 1. Borrow is not required. 1 minus 1, difference is 0. Borrow is not required. I hope everything is clear. So we are calculating what is the difference, what is the borrow out. For the subtraction, if it is required to take borrow, we are saying that borrow is required. We are mentioning it as output borrow is there. Now, then find Boolean expression for outputs in terms of input variables. D is equals to, what is that? AB01, AB10. What is it here? A bar B plus AB bar, which is A XOR B. Then borrow out is what? A bar B. When AB01, output is 1, which is A bar B. Then writing the cycle. XOR difference and borrow. A XOR B is difference, borrow out is A bar B for A minus B operation of subtractor. Next, moving to next slide. I'm moving to next slide. Full subtractor. Full subtractor. Full subtractor. What is it here? Here we are considering input borrow also. Same as a full adder. Here, full subtractor, we are considering input borrow also. What is it? Let us see. So A, B, and input borrow. 3 inputs are there. What about output? Difference and borrow. Difference and borrow out. Check it correctly. A, B, B, I are inputs. Now outputs are difference and borrow out. Difference and borrow out. I will explain what is input borrow and output borrow difference. Before that, let me write the input combinations. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. 1, 1, 1. 0, 0, 0 to 1, 1, 1. Now, operation is A minus B minus BI. Why? Let us understand. Please, some of you may be knowing, please bear with me to understand this concept. What is input borrow? What is output borrow? I am subtracting. Decimal number, subtracting. 8 minus 5, 3. 2 minus 4 cannot be subtracted. 2 minus 4 cannot be subtracted. Then what we do? Taking borrow. Then it becomes a 12. 12 minus 4, it is 8. What we have here? What we have here? 2. Why it is becoming 2? Already there is a borrow. Already there is a borrow. That is the reason it is becoming 2. So, what is A here? 3. What is B here? 9. Why it is becoming 2 minus 9 instead of 3 minus 9? There is a borrow already from this. So, borrow already taken from this is called input borrow. So, to get effective value A minus BI, it is 3 minus 1, it is 2. Why? There is a borrow already taken from this. That is called input borrow. So, to get effective value, we are saying that A minus BI. What is BI? Borrow already taken from that is called input borrow. Now, the effective value is 2. 2 minus 1, 2 minus 9 cannot be subtracted. We need to take borrow. It becomes now 12. 12 minus 9, which is a 3. So, for this subtraction, we are taking borrow from next. That is called output borrow. For this position, already borrow taken. That is input borrow. And for this subtraction, we have to take borrow from next. That is called output borrow. A simple way is right, let me complete that. What is it here? It is 6, but effective value is 5. Why? Already borrow taken from this. That means input borrow is 1. A is 6. Input borrow is 1. 6 minus 1, it is 5. 5 minus 2, it is 3. 5 minus 2, it is 3. So, what is input borrow? Borrow already taken from that. What is output borrow? Borrow required for the subtraction. So, output borrow is borrow we are getting from next. What is input borrow? Borrow already taken from this position. So, to get effective value of A, we do that A minus BI. In that, we are subtracting B. So, A minus BI minus B. For this subtraction, if it is required to take borrow, that we are getting from next, that is called output borrow. Once again, to get effective value of A, you need to subtract input borrow from that. If input borrow is there, A minus BI, effective value. A minus BI is effective value minus B. For this subtraction, if it is required a borrow, that we are getting from next, it is output borrow. It is output borrow. For each and every position, if you are observing, in this position, it is not taken borrow. That means input borrow is 0. Are we getting borrow from next? No. So, for this position, input borrow is 0, output borrow is 0. For this position, input borrow is 0, output borrow is 0. Why? It is not taken borrow from this. We are not taking borrow from next. So, for this position, input borrow is 0, output borrow. For this position, it is not taken any borrow from this. It is not taken any borrow from this. So, input borrow is 0. What about output borrow? Yes, we are taking borrow from next. So, output borrow is there. So, for this position, input borrow is 0, output borrow is 1. And for coming to this one, what is it here? Input borrow is 1 because borrow is already taken from this. So, input borrow is 1. And we are taking borrow from next. So, output borrow is 1. So, for this position, input borrow is 1, output borrow is 1. And for this position, input borrow is 1, output borrow is 0. Output borrow is 0. Finally, what we are performing, A minus BI minus B. Or we can say A minus B minus BI also. Simple thing. So, if already borrow taken, that must be subtracted from A. And from that, we need to subtract B. That is the reason we are saying that here we are having 2. Why we are saying 2? Already borrow taken. That is subtracted from A. A equals to 3. But borrow is there from this. So, it becomes effective value is 2. From that we are subtracting B is 9. For this subtraction, we need to take borrow from next. That means output borrow is 1. What is that here? A minus B minus BI. Operation is what? A minus B minus BI. Check it correctly. So 0 minus 0 minus 0. Difference is 0. Borrow is not required. So output borrow is 1. 0 minus 0 minus 1. Yes, borrow is required. Check it correctly. For 0 minus 0 minus 1 cannot be subtracted without borrow. So output borrow is 1. After taking borrow, it becomes now 0 plus base value. What is base value? 2. 0 plus 2 is 2. 2 minus 0 minus 1. Difference is 1. Clear? So 0 minus 0 minus 1 cannot be subtracted. That is the reason borrow is required. After taking borrow, it becomes now 0 plus base value. What is base value? 2. 0 plus 2 is 2. 2 minus 0 minus 1. Difference is 1. Yes. 0 minus 1 minus 0. A minus B minus BI. 0 minus 1 minus 0. Borrow is required. After taking borrow, it becomes now 0 plus base value 2. 2 minus 1 minus 0. It is a 1. 0 minus 1 minus 0. Borrow is required. After taking borrow, 0 plus base value. What is base value? 2. So 0 plus 2 is 2. 2 minus 1 minus 0. Difference is 1. Yes. 0 minus 1 minus 1. Borrow is required. Check it correctly. Borrow is required. Now 0 plus base value 2. 2 minus 1 minus 1. Difference is what? 0. Check it correctly. 0 minus 1 minus 1. Borrow is required. After taking borrow, 0 plus base value. What is base value? 2. 0 plus 2 is 2. 2 minus 1 minus 1. Difference is 0. 1 minus 0 minus 0. Borrow is not required. What about difference? 1. 1 minus 0 minus 1. Borrow is not required. What is difference? 0. 1 minus 0 minus 1. Now 1 minus 1 minus 0. Borrow is not required. Difference also 0. 1 minus 1 minus 1. Borrow is required. After taking borrow, listen carefully, last one. 1 minus 1 minus 1, borrow is required. After taking borrow, 1 plus base value. What is base value? 2. 1 plus 2 is 3. 3 minus 1 minus 1. Difference is what? 1. Once again, last one. 1 minus 1 minus 1. Borrow is required. After taking borrow, 1 plus base value. What is base value? 2. 1 plus 2 is 3. 3 minus 1 minus 1. Difference is 1. So, after this, let us write a Boolean expression for outputs in terms of input variables. In terms of input variables. Writing Boolean expression for outputs in terms of input variables. Right. Now, before that, let me give input combination numbers for ABBI. So 0, 1, 2, 3, 4, 5, 6, 7. Then difference is equals to sigma m of what we have here 1, 2, 4, 7. Borrow out is equals to sigma m of what is it here 1, 2, 3, 7. Find Boolean expression for outputs in terms of input variables. Simple thing is using K-map. Variables are A, B, B, I. Once again, for difference, if you are observing A, B, B, I, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 2, 4, 7. Once again, it is 3 input XOR. Difference is equals to A XOR, B XOR, BI. Then once again, if you are using another K-map for borrow out with variables A, B, BI, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. What is the numbers? 1, 2, 3, 7. Grouping 1, 2, 3. Sufficient. So borrow out is equals to A bar B plus BBI plus A bar BI. A bar B plus BBI plus A bar BI. Then XOR. A B BI. Complete the circuit. Very simple. Everyone can do that without my help also. A bar B B BI and A bar BI. Differential bar out. This is a full subtractor, half subtractor and full subtractor. Right. That is a half subtractor and a full subtractor. Right. Let me take a small break. After break, we'll continue. Right. Welcome back. We have discussed one bit adder, one bit subtractor. In adders, in one bit adder, once again we have discussed off adder and full adder. In one bit subtractor, we have discussed half subtractor and full subtractor. Now, let us get into right. I hope you can try that implementing full adder using off adders and required logic gates. Full adder implementation using off adders. Sorry, full adder implementation using off adders and logic gates we have discussed. And the remaining is full subtractor using half subtractors and required logic gates. Complete that implementation also. Complete that implementation also. Later, if you find any difficulty, let me know. I'm there to help you. Now, let us see one more concept, comparator. And comparator, which is comparing two inputs, which is comparing two inputs. That results maybe one may be greater than other, one may be lesser than other, one may be equal to other. There are three possibilities. When you are comparing two inputs, the possibilities are one may be greater than other, one may be lesser than other, one may be equal to other. These are possibilities on comparator output. In this comparator also, we have again 1-bit comparator, 2-bit comparator, or n-bit comparator also. Let us start with first 1-bit comparator. 1-bit comparator. 1-bit comparator. Right, 1-bit comparator. It is comparing two inputs of 1 bit, which can be A and B. A and B. What can be the outputs? A greater than B, A less than B, A equal to B. A greater than B, A less than B, A equal to B. You can represent like this also. A greater than B, A less than B, A equal to B. A greater than B, A less than B, A equal to B. AB possibilities can be 0, 0, 0, 1, 1, 0, 1, 1. These are possible AB combination. AB 0, 0, 0, 1, 1, 0, 1, 1. Now, when you are comparing magnitude, AB 0, 0, A greater than B is false. A less than B is false. A equal to B is true. A equal to B is true. Because A is 0, B is 0. If you are comparing magnitude, A equal to B is true. For AB 0, 1, A greater than B is false. A less than B is true. Why? A is 0, B is 1. A less than B is true. And again, A equal to B is false. For 1, 0, A greater than B is true. A less than B is false. A equal to B is false. For 1, 1, A greater than B is false. A less than B is false. A equal to B is true. That's it. What is here? A greater than B, A less than B, A equal to B. Now, after specifying outputs, writing Boolean expressions, A greater than B is 1 for AB 10 means AB bar. A less than B, AB 01, A less than B is 1 means A bar B. A equal to B is 1 for AB 00, AB 11. That means A bar B bar plus AB, which is A XNOR B. A XNOR B. A XNOR B. Then what is the circuit for this is A. Let me take bubble. It is A greater than B. It is A less than B. It is A equal to B. Circuit. A B bar, A bar B, A XNOR B. A XNOR B. That is a one bit comparator. One bit comparator. Moving to next slide. Simple thing. Comparing magnitude of A and B. AB00, A equal to B is 2. AB01, A less than B is 2. AB10, A greater than B is 2. AB11, A equal to B is 2. With that, if you are writing expressions, A greater than B is AB bar, A less than B is A bar B, A equal to B is A XNOR B. Already we know this A XNOR B. Two input XNOR is resulting output one when two inputs are same, coinciding, equal. I hope you know already this, sir. While discussing XNOR gate, I have clearly mentioned that two input XNOR gate output is 1 when two inputs are equal, right? Coinciding, same. Right. If I say 2-bit comparator, what is 2-bit comparator? A is of 2 bits A1, A0, B is of 2 bits B1, B0. Now, A greater than B, A less than B, A equal to B. Once again, 2-bit comparator. A is of 2 bits, B is of 2 bits. Then 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0. Lal Krishna. What happened? 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. If I write outputs for 0, 0, 0, magnitude if you are comparing, it is equal is true. If A is 0, 0, B is 0, 1 means A is less than B. For A is 0, 0, B is 1, 0. What is that here? Again, A less than B. A is 0, 0, B is 1, 1 means again A less than B. And 0, 1, 0, 0, A is greater than B. 0, 1, 0, 1, again A equal to B. 0, 1, 1, 0, A less than B. Right. See, for AB 0, 1, 1, 1, again A less than B. 1, 0, 0, 0, A greater than B. 1, 0, 0, 1, A greater than B. 1, 0, 1, 0, A equal to B. 1, 0, 1, 1, then A less than B. 1, 1, 0, 0, A greater than B. 1, 1, 0, 1, A greater than B. 1, 1, 1, 0, A greater than B. 1, 1, 1, 1, A equal to B. A equal to B. These are possibilities. As it is 2-bit comparator, you are writing all this. If I say 4-bit comparator, 4 bits of A, 4 bits of B. If I say 4-bit comparator, 4 bits of A, 4 bits of B, total 2 power 8 combination, that is 256 combinations I need to write. And it is not possible to analyze in this conventional method. Then what I can do? What we can do? If I say A1, A0, B1, B0, simple observations, check it correctly. If A1 greater than B1, that means if A1 is 1, B1 is 0. Check it correctly. What is it here? Condition is A1 greater than B1. If A1 is greater than B1, then I don't need to check about A0, B0, right? If A1 is 1, B1 is 0, A0, B0 can be 0, 0, 0, 1, 1, 0, 1, 1. Whatever it is that A0, B0, no doubt A greater than B will be true. Verify that. If higher order bits are compared. If higher order bits are satisfying the greater, irrespective of other bits, A greater than B is true. Am I right? Any doubt in that? Yes or no? When A1 greater than B1, irrespective of A naught, B naught, A greater than B is true. Any other possibilities? Yes, sir. When A1 is equals to B1, that means 0, 0 or 1, 1. When A1 is equals to B1, other possibility is A naught is 1, B naught is 0. A naught is 1, B naught is 0. Check it correctly. When A1 is equals to B1 can be 0, 0 or 1, 1. Two possibilities. Simple way is check it. Decimal 64, 37. A and B. A greater than B is true. In this, what we are observing? A1 greater than B1. What about this? Irrespective of other digits. Irrespective of other digits, A1 greater than B1 is satisfying. Then A greater than B is true. Other possibility 64, 62. Then also A greater than B is true, right? So, or when A1 is equals to B1 is satisfied, A naught greater than B naught. Any other conditions for getting A greater than B? No. If A1 is greater than B1, irrespective of A naught, B naught, A greater than B is true. Because this is greater than this. Do I need to check about this? No. When these two are equal, then we need to go with second possibility. What is that here? The second digits we need to compare. To get A greater than B, A naught must be greater than B naught. If A1 greater than B1, when A1 greater than B1, irrespective of A naught, B naught, A greater than B is true. If A1 is equals to B1 is satisfied, then again, second condition is A naught greater than B naught. A naught greater than. See, here also, what is it here? A1 greater than B1. In binary, what we can have? A1 is 1, B1 is 0. Irrespective of A naught, B naught means 0, 0, 0, 1, 1, 0, 1, 1. When coming to second condition, A1 equals to B1 means in binary, what can be the possibilities? Either 0, 0 or 1, 1. And when A1 equals to B1 is satisfied, A naught is greater than B naught. A greater than B is. Right? Once again, try to understand these correctly. Once again, I'm explaining with whatever we are discussed with respect to decimal. If you are observing possibilities for getting A greater than B is true. If you are observing possibilities for getting A greater than B is true, what is the first condition? A1 greater than B1, irrespective of A naught, B naught. Means A1 is 1, B1 is 0. A naught, B naught can be 0, 0, 0, 1, 1, 0, 1, 1, irrespective. So A1 is 1, B1 is 0. A1 is 1, B1 is 0. A1 is 1, B1 is 0. Irrespective of A naught, B naught, A greater than B is true. What is second condition? Or when A1 is equals to B1 is satisfied, simultaneously A naught is greater than B naught. A1 equals to B1. A1 equals to B1 in how many ways? 0, 0, 1, 1. A1 is equals to B1 in two ways. Because in binary, zeros or ones. If when this is satisfied, what is second condition simultaneously? A naught greater than B naught means A naught is 1, B naught is 0. A naught is 1, B naught is 0. For these also, A greater than B is true. For these also, A greater than B is true. Are you following? These are the 6 combinations only A greater than B is true in this table. 1, 2, 3, 4, 5, 6. Verify that. These are the 6 combinations for which A greater than B is true. Right. This is a greater than B conditions. Now we need to write expression. What is here? A1 greater than B1 irrespective of A naught, B naught. That means A1 greater than B1 means A1 is 1, B1 is 0. That is A1, B1 bar. Irrespective of A naught, B naught. Irrespective of A naught, B naught means A naught, B naught are existing in 0, 0, 0, 1, 1, 0, 1, 1. So two variables are existing in 2 power 2 combinations. Those can be adjacent in the K map. Those two variables combinedly can be eliminated. Yes, resulting 1. Am I right? So irrespective of A naught, B naught, that means A naught, B naught are existing in 0, 0, 0, 1, 1, 0, 1, 1. Two variables are existing in 2 power 2 combinations. Then two variables can be eliminated combinedly. Right? Or logically, or A1 equals to B1. How to check that A1 equals to B1? A1 XNOR B1. A1 XNOR B1. Then A naught greater than B naught means A naught is 1, B naught is 0. A naught is 1, B naught is 0. That is a Boolean expression for A greater than B. Right? First condition is what? A1 greater than B1. That means A1 is 1, B1 is 0. Irrespective of A naught, B naught, then A naught, B naught are eliminated. Or, logical or. A1 equals to B1. How to check? XNOR. And A naught greater than B naught means A naught is 1, B naught is 0. Right? So, if you are not accepting this, let me take another way. Check it correctly. So, after writing combinations for which A greater than B is 1 in the table, what we can write? See, here it is 1. A1, A naught bar, B1 bar, B naught bar, plus A1, A naught bar, B1 bar, B naught, plus A1, A naught, B1 bar, B naught bar, A1, A naught, B1 bar, B naught. So, in these four, if you are observing, A1, B1 bar common. Then A naught bar, B naught bar, plus A naught bar, B naught, plus A naught, B naught bar, plus A naught, B naught. A naught bar, B naught bar, plus A naught bar, B naught, plus A naught, B naught bar, plus A naught, B naught. Plus these two. What is it here? A1 bar, A naught, B1 bar, B naught bar, plus A1, A naught, B1, B naught bar. So if you are observing A naught, B naught bar, A naught, B naught bar common in this, then A1 bar, B1 bar, plus A1, B1, and with A naught, B naught bar. Fine. And what about this term? Right. What about this term? What is this term? 1. Why? A naught, B naught are existing in 0, 0, 0, 1, 1, 0, 1, 1. Or in these two, I can take A naught bar common, B naught bar, B naught, 1. B naught bar plus B naught is 1. Again, A naught common, B naught bar plus B naught is 1. So, A naught bar plus A naught, again 1. So, finally, we are getting expected. What is that? A1, B1 bar and with 1 same, plus here A1 bar, B1 bar plus A1, B1 is nothing but A1 XNOR B1 and with A naught, B naught bar. Even though you are writing expressions, it will be same. That is the reason all this is not required, unnecessary. Now onwards, we don't write all these tables also. Simply, we are going to do that. Let us see what is it here. First, A greater than B condition for 2-bit comparison. What is that? Please help me. A1 greater than B1, irrespective of A naught, B naught, A greater than B is 2. Or when A1 is equals to B1, simultaneously, what is second condition? A naught greater than B naught. Bit by bit comparison. Now, what is the expression for this condition? A1, B1 bar. Or A1 equals to B1 means XNOR. And with A naught greater than B naught means A naught, B naught bar. That's what we are writing. Once we are writing conditions, writing expressions is easy. Now tell me what is the conditions for A less than B first? Exactly reverse. Wherever greater is there we write lesser, because A1 less than B1, A less than B is true. A1 less than B1, that means higher order bits are compared. If higher order bit of A is lesser than higher order bit of B, then obviously irrespective of other bits, A less than B is true. Then A1 less than B1 satisfied. Then irrespective of A naught, B naught, A less than B is true. Or when A1 equals to B1 is satisfied and A naught is less than B naught. Right? So let us write expression here. A1 less than B1 means A1 is 0, B1 is 1. A1 bar B1 or A1 equals to B1 means A1 XNOR B1 and with A0 less than B0 means A0 is 0, B0 is 1. A0 bar B0. Right. Now A equal to B. Help me. Conditions. A1 is equals to B1 and A0 is equals to B0. Respective bits are equal, sufficient, right? A1 equals to B1, A0 equals to B0. A1 equals to B1 can be written as A1 XNOR B1 and with A0 XNOR B0. That is expression for A equal to B. A1 XNOR B1 and with A0 XNOR B0. Writing all this table also we are getting same. If you are going with condition bit by bit comparison, MSB to LSB also will be same. So once again, I'm showing that the comparator, 2-bit comparator. This is what we are doing. Same thing. We are going with the conditions and writing. A1 equals to B1. How many ways? 0, 0, 1, 1. Two possibilities. A0 equals to B0. Again 0, 0, 1, 1. Two possibilities. Then we are getting 4 possibilities. That's what we are seeing here. 1, 2, 3, 4 combinations. A equal to B is true. A greater than B is true for 6 combinations. A less than B is true for 6 combinations. A equal to B is true for 4 combinations. Total 6 plus 4, it is a 16. Now, please try. A is of 4 bits. B is of 4 bits. Write the Boolean expression for A greater than B, A less than B, A equal to B. A greater than B, A less than B, A equal to B. Akash, 1001 is not A equal to B. A is 10 is 2 decimal equivalent. B is 01, it is 1. 2 is greater than 1. For 1001, it is A greater than B. Akash. A is 4 bits, A3, A2, A1, A0. B is 4 bits, B3, B2, B1, B0. What is the Boolean expressions for A greater than B, A less than B, A equal to B? What are the Boolean expressions for A greater than B, A less than B, A equal to B? Don't write the combinations, go with the conditions. If I write conditions for A greater than B, help me. A3 greater than B3. Do I need to check remaining bits? No. When MSB is satisfying A3 is greater than B3, I don't need to check about remaining bits, irrespective of all other bits. A greater than B is true. Or next possibility is when A3 is equals to B3 is satisfied, simultaneously A2 must be greater than B2. Next bit we are comparing. To compare next bit, what we are expecting, these bits must be equal. Then we go for next bit. Or when A3 is equals to B3 and A2 is equals to B2 and A1 greater than B1. When these two bits are equal, we go for third bit comparison. Or what is next possibility? When these three bits are equal to these three bits, we go for comparison of LSB. What is it here? A3 is equals to B3 and A2 is equals to B2 and A1 is equals to B1 and A0 is greater than B0. Right? So A3 greater than B3 means what? A3, B3 bar, irrespective of all, eliminated. Or when A3 equals to B3, that means XNOR and with A2 greater than B2, A2, B2 bar plus when A3 equals to B3, XNOR A2 is equals to B2, XNOR A1 greater than B1 means A1, B1 bar. Or what is that next one? A3 is equals to B3, XNOR A2 equals to B2, XNOR A1 is equals to B1, XNOR A0 greater than B0 means A0, B0 bar. That's it. Once you're writing conditions, nothing is there. Now, A less than B. I'm writing expression directly. A3 less than B3. A3 bar B3. Or when A3 is equals to B3, XNOR A2 less than B2. That means A2 bar B2. Or when A3 is equals to B3, XNOR A2 is equals to B2, XNOR A1 less than B1. That means A1 bar B1. Or when A3 is equals to B3, A2 is equals to B2, A1 is equals to B1, A0 is less than B0 means A0 bar B0. Right? Now, A equal to B. Very simple. What is it? A3 is equals to B3, XNOR. A2 is equals to B2, XNOR. A1 is equals to B1, XNOR. A0 is equals to B0, XNOR. That's it. Respective bits are equal simultaneously. A3 equals to B3 and A2 equals to B2 and A1 equals to B1 and A0 equals to B0. Can you say how many combinations A equal to B can be true? A3 equals to B3, two possibilities. A2 equals to B2, two possibilities. A1 equals to B1, two possibilities. A0 equals to B0, two possibilities. Total 16 combinations. It will be A equal to B in 4-bit comparator. In 4-bit comparator. 16 combinations. Why? A3 equals to B3, two possibilities. A2 equals to B2, two possibilities. A1 equals to B1, two possibilities. A0 equals to B0, two possibilities. Total 16 combinations. A equal to B is true. Very simple. I'm moving to next slide. Bit to by bit comparison, MSB to LSB. Question, try. The total number of combinations for which A greater than B is true in 5-bit comparator is dash. What is the answer? Very good. That's what I'm going to do. Chakrabarti. Here someone is asking how it is 16. A3 equals to B3. How many possibilities? 0, 0, 1, 1, 2 possibilities. A2 equals to B2. How many possibilities? 2 possibilities. A1 equals to B1. Again 2 possibilities. A0 equals to B0. 2 possibilities. Total 16 possibilities are there for which A equal to B in 4-bit comparator. Right. Very simple question. No need to struggle. Let us see how we solve this. 5-bit comparator means 5 bits of A, A4, A3, A2, A1, A0. 5 bits of B, B4, B3, B2, B1, B0. How many combinations total? 5 variables plus 5 variables. Total 10 variables. So how many combinations, sir? 2 power 10 combinations. 2 power 10 combinations possible. Total combinations possible is a 2 power 10. Understand correctly? Yes. Many are answering correctly. Very good. Very good. Okay. Understand correctly. What is it here? Total 10 variables. How we are getting 10 variables? 5 variables of A, 5 variables of B. Total 10 variables. Total number of combinations to power 10. To power 10. In these, how many are equal? A4 is equals to B4. How many possibilities? 2 possibilities. A3 equals to B3. How many possibilities? 2 possibilities. A2 equals to B2. Again, 2 possibilities. A1 equals to B1. Again, 2 possibilities. A0 equals to B0. Again, 2 possibilities. To power 5. Right? So, total combinations minus equal combinations. What will be there? Greater or lesser, right? In total combinations, yes, Deepa, wait. In total combinations, I am excluding equal combinations. How am I getting equal combinations? 5-bit comparator. Equal means bit by bit if you are comparing, A4 equals to B4, 2 possibilities, A3 equals to B3, 2 possibilities, A2 equals to B2, 2 possibilities, A1 equals to B1, 2 possibilities, A0 equals to B0 is also 2 possibilities. Yes. Total 2 power 5 combination, it is equal. Total minus equal. Remaining will be greater or lesser. Half will be greater, half will be lesser. Half will be greater, half will be lesser. So if I take half of this, that is a greater or lesser combinations. How much is that? 1024 minus 32 divided by 2. Calculate, it will be 496. 496 combination A greater than B, 496 combination A less than B. And how many combinations A equal to B? 2 power 5. Just now we have done. It is a 32. It is 32. Once again, 5-bit comparator, 5 bits of A, 5 bits of B, total 10 variables. Then total combination will be 2 power 10. In that equal combination is obviously 2 power 5. Total minus equal. Remaining is what? Greater and lesser. Of is greater, of is lesser. The reason total minus equal divided by 2 is giving greater as well as lesser. Equal combination is nothing but 2 power 5, which is 32. Right. Let us generalize this also. What is it? If I take n-bit comparator, help me, n-bit comparator, right? A n minus 1 to A naught. How many variables? N variables. B n minus 1 to B naught. How many variables, sir? N variables. How many total variables, sir? 2 power 2n. How many variables? 2n variables. Total combinations, 2 power 2n. In these, how many can be equal? Respective bits. Equal, equal, equal. That is a 2 power n combination. So total combination is 2 power n. 2 power 2n. 2 power 2n. Why? N variables of A, n variables of B, total 2n variables. Total number of combinations can be 2 power 2n minus equal combinations how many? 2 power n divided by 2. What is this? Greater or lesser? If I go with equal combination, what is it? 2 power n. 2 power n. If anyone is having any doubt, please report in the Q&A about this. Yes, many have answered correctly. Yes. After understanding this n-bit comparator, Ashutosh, how equal is 2 power n? Shilpa, yes. See, A4 equals to B4, 2 possibilities. A3 equals to B3, 2 possibilities. A2 equals to B2, 2 possibilities. A1 equals to B1, 2 possibilities. A0 equals to B0, 2 possibilities. 2 is multiplied for 5 times, it is 2 power 5 for 5-bit comparator. Just understand correctly. So instead of right, oh something nothing has happened. Very simple. So 5-bit comparator 2 power 5 combinations. Here 4-bit comparator, it is 2 power 4 combinations. N-bit comparator, equal combinations can be 2 power n. For 4-bit 2 power 4, for 5-bit 2 power 5, an minus 1 is equal to bn minus 1, 2 possibilities. An minus 2, bn minus 2, 2 possibilities. So and so a naught equals to b naught, 2 possibilities. 2 is multiplied for how many times? N number of times. That is 2 power n. Total 2 power 2n minus equal to power n. So half will be greater, half will be lesser. Yes, equal is 2 power. Ashutosh. Yes, I'll show you that. Yes. G is greater, L is lesser, E is equal. That's good. 5-bit comparator means 5 bits of A, 5 bits of B. What is required to mention inputs? Please mention correctly what is the question. Bhavani, substitute. 2-bit comparator greater you want to know. N equals to 2. 2 power 2 into 2 minus 2 power 2 divided by 2. Am I right? 2 power 4, 16 minus 2 power 2 is 4 divided by 2. How much is that? 6. That's what we have seen earlier also. Bhavani. Right. Now, next is a n-bit adder. N-bit adder. Example 4-bit adder. What is it here? Let us see. A3, A2, A1, A0. 4 bits of A. 4 bits of B, B3, B2, B1, B0. A3, A2, A1, A0, B3, B2, B1, B0. Now we are adding these two. Then what we do? A0 plus B0 producing some S0 and producing carry for next bit, right? Output carry. For this position, output carry C1. Now C1 plus A1 plus B1. What is it here? S1 producing carry C2. I think no one is having any doubt. Just adding C1 plus A1 plus B1 is producing S1 carry C2. C2 plus A2 plus B2 is a S2 producing carry C3. C3 plus A3 plus B3 is a S3 and producing carry C out. Final carry out. Right? So this is 4-bit adder. If you are having n bits, extending again. For example, if I would like to implement this 4-bit adder using 1-bit adders, which we know already. To implement this 4-bit adder, if I use 1-bit adders, which I know already, in A0, B0 position, do I need to use off adder or full adder? Please respond in the chat box. In A0, B0 position, do I need to use off adder or full adder? Yes, 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 because we have only A0, B0. What is it here? Off adder is sufficient. Yes, please stop, right? So I'm using off adder. With inputs, what is that? A0, B0, which produces some S0. And in A1, B1 position, do I need to use off adder or full adder? Here it is, full adder. Why? It is adding 3 inputs. It is a full adder, which is accepting C1 from this, which is accepting A1, B1 also. In this position, compulsory I need to use full adder, which is producing S0. Here it is S1. And again, next bit position, again, full adder only. Again, full adder only. Yes, again, full adder. Which is accepting inputs A2, B2, and here it is C2. Producing S2. And also, in the next bit position, what do we have here? Again, full adder. A3, B3, and here we have C3. Producing S3. Here it is C out. What is the conclusion? 1 off adder, 3 full adders required to implement 4-bit adder. 1 off adder, 3 full adders required to implement 4-bit adder. If I would like to implement a n-bit adder, 1 off adder, plus n minus 1 full adders. One off adder, n minus 1 full adder. This is a optimal implementation. Once again, what is it here? While implementing 4-bit adder, what we observed in 0th bit position, off adder is sufficient because we have only A0, B0 inputs. So in the next bit position, compulsory I need to use full adder, which is confirming that to implement 4-bit adder, one off adder, 3 full adders required. Similarly, n-bit adder can be implemented using one off adder and n minus 1 full adders, right? But it may be facing some problems when you are implementing like this. What are the problems? Let us see. What is it here? Let us see. See, if I am implementing 8-bit adder, what do you mean by this? 8 bits of A, A7, A6, A5, A4, A3, A2, A1, A0. And again, B7, B6, B5, B4, B3, B2, B1, B0. Understand correctly? One important concept I'm going to address. So if you're adding this, what we get here? S0, C1, S1, C2, S2, C3, S3, C4, S4, C5, S5, C6, S6, C7, S7, Cout. This is 8-bit adder. Now this 8-bit adder, I would like to implement using 2 4-bit adders. This 8-bit adder, I would like to implement using 2 4-bit adders. Then what I can do? 1 4-bit adder. Understand correctly? 1 4-bit adder. Four-bit adder. Here it is accepting 4 bits of A, that is A3, A2, A1, A0. And here 4 bits of B. What is it here? B3, B2, B1, B0. Producing S3, S2, S1, S0. And one more 4-bit adder for higher nibble. One more 4-bit adder for higher nibble, in which it is accepting higher order bits. What is it here? A7, A6, A5, A4, and also B. B7, B6, B5, B4, producing S7, S6, S5, S4. But what we are missing? Interlink between these two. That means whatever C4 is produced must be accepted as input carry. But in this implementation, we don't have any input carry. So instead of implementing using off adder and n-1 full adders, better to go with n full adders. To get some applications of n-bit adder, better to go with n full adders. In this, what we are saying here, if you require, we can use, otherwise we can neglect about C0. So better to have an input carry also C0. So here also it is full adder. Optimally, yes, whatever we have done earlier is correct. But for getting some applications, then we need to go with the n full adders. So with input carry, this n-bit adder is giving some applications. What are those applications? Let us see. So understand correctly what is here? Optimally, or if it is asked what is the minimum number of adders required, means what is the optimal implementation, means one off adder, n-1 full adders. But if I am implementing using n full adders, n-bit adder, if I am implementing n-bit adder using n full adders, I am going to see some applications of n-bit adder. So what are the applications we see? First, assume there is an input carry. If it is required, we can use. Otherwise, we make it 0, not a problem. So if you make C naught is 0, whatever the addition we have done earlier will be getting, not a problem. Not a problem. So let me take it full adder 0, full adder 1, full adder 2, full adder 3. So once again, what we have done here, optimal implementation is 1 off adder, n minus 1 full adder. But practically to get applications, we are getting n full adders. Yes. After this, what is the conclusion? We are using n full adders. Understand correctly? N full adders. Full adder 0 with A naught, B naught, C naught inputs, producing S naught and also carry C1. Again here, one full adder 1 with A1, B1 and here C1 producing S1 and also carry for next stage. Full adder 2. Here inputs are A2, B2, C2. It is S2. Right. This is a n bit adder using 1 bit adders. This is n bit adder using 1 bit adders. Yeah, Triveni, we cannot say compulsory carry will be there. If carry is there, what we do? Question is A naught, B naught position. Compulsory is it giving carry means? What it means? So if it is giving carry, what do you do? I cannot guarantee there will be carry. If there is a carry, for example, A naught, B naught is 1, 1. Triveni, A naught, B naught is 1, 1. What will be C1, can you say? Or are you saying about C naught? Then, if it is about C1, if A naught, B naught is 1, 1, right, there will be carry, right? If carry is there, we need to pass it. If carry is not there, 0, it's not a problem. But whenever there is a carry, can we neglect that? When carry is 0, that C1 is becoming 0. From A naught, B naught, if carry C1 is 0, no problem. But if C1 is 1, then it must be added to the next bits. Triveni, right? Right. Okay. All the doubts, right? You will get clarity, right? Triveni, I'll talk to you at the end, please. I'll talk to you at the end. Right, right. Fine. So in this adder, let me say that each full adder is taking delta time to stabilize the output. From the point inputs applied, a full adder is getting delta time to stabilize the output. Once again, if a full adder is taking delta time to stabilize the outputs, then what will be the propagation delay of this 4-bit adder? In this, if you are observing, A naught, A1, A2, A3, B naught, B1, B2, B3, and C naught are applied on parallel pins. What is it here? A naught, A1, A2, A3, B naught, B1, B2, B3, and C naught. We have parallel pins to apply the inputs. That means I can apply all these inputs at 0 time. So as we have a parallel pins to apply the inputs and also S3, S2, S1, S0 and C out are parallel pins to observe the result or sum. Once again, what is it here? We have parallel pins to apply the inputs. We have parallel pins to observe the result. So finally, parallelly we are applying inputs. Parallelly we are getting outputs. To apply inputs, we have parallel pins. To observe the result, we have parallel pins. It is a parallel adder. It is a parallel adder. So what we are discussing is a parallel adder. Reason for saying parallel adder is parallelly we are applying inputs on parallel pins and parallelly we can observe the result on parallel output pins. So it is not serial. What do you mean by serial? Applying bit to by bit. That is called serial. Applying all the bits parallelly. So parallelly we are applying inputs. Parallelly we are observing the result. Yes. If a full adder is taking delta time to produce its output from the point inputs applied. If a full adder is taking delta time to produce or to stabilize the outputs from the point inputs applied, then what will be the propagation delay of this 4-bit adder? What will be the propagation delay of n-bit parallel adder? Listen. So what we need to analyze? Full adder 0 is getting A0, B0, C0 at what time? 0 time. Then S0, C1 will be stabilized in how much time? Delta time. Because the full adder is taking delta time. Full adder is taking delta time. Once again, full adder 0 is getting A0, B0, C0, all these at 0 time. This full adder is taking delta time to produce S0 and C1. Full adder 1 is getting A1, B1 at 0 time. But C1 is not there. C1 is stabilizing in worst case delta time. Once again, full adder 1 is getting A1, B1 at 0 time, but C1 is not ready. C1 is taking delta time to get ready. So time required to stabilize all the inputs here, how much? Whichever is maximum, right? If you remember, delta. So then onwards, this full adder 1 is taking another delta time to produce S1 and C2. At what time? 2 delta. Anyone is having any questions? Full adder 1 is getting A1, B1 at 0 time, but C1 is getting ready at delta time. All the inputs are ready by delta time. To produce output, again full adder delay means S1 and C2 will be ready by 2 delta. So full adder 2 is getting A2, B2 at 0 time. Full adder 2 is getting A2, B2 at 0 time, but C2 is stabilizing at 2 delta. The time required to stabilize all the inputs of full adder 2 is how much time? 2 delta. Then onwards, it takes another delta time to produce S2 and C3. So these will be ready by 3 delta. Full adder 3 is getting A3, B3 at 0 time, but C3 is taking 3 delta time in worst case. The time required to stabilize all the inputs of full adder 3 will be 3 delta. Then onwards, this full adder is taking another delta time to produce S3 and C out, means it is a 4 delta. It is a 4 delta. It means T4 bit is equals to 4 delta. Then Tn bit is equals to, what is that? N delta. Is a N delta. Tn bit is equals to N delta. This is a parallel adder if a full adder is taking delta time. The full adder is taking delta time to produce the outputs. To produce the outputs, it is taking delta time from the point inputs applied. Then n bit adder, parallel adder delay is n delta. N delta. Yes. Right. That is T n bit is equals to n delta. Delta is full adder delay. Listen to me carefully when I'm explaining. Delta is time required to stabilize the outputs from the point input stabilized. So, delta is the time required to stabilize the outputs from the point input stabilized. From the point input stabilized. Now, full adder. I'm analyzing now full adder. Full adder is consisting of what? Two parts. One is a sum circuit. Understand correctly? We are getting into next level, sir. And another one is a carry circuit. Another one is carry circuit. So here it is a sum circuit. When you are applying ABCI inputs, the full adder is responding to these inputs with two different circuits. One is sum circuit, other one is carry circuit. Am I right? So from the point input supplied, listen carefully. From the point input supplied at 0 time, if sum circuit delay is TS, carry circuit delay is TC. What is delta now? Full adder delay. What is delta? Should say that from the point input supplied, if it is taking TS time to produce sum, TC time to produce carry out, what is the delta? Maximum of TS comma TC. Maximum of TS comma TC. I hope everyone is understanding. So delta is full adder delay, which is nothing but maximum of TS comma TC. Yes, very good. Maximum of TS comma TC. Delta is maximum of TS comma TC. But in this, if you are observing clearly, when I know carry circuit delay separately and sum circuit delay separately in a full adder, so here full adder one is waiting for both S0 and C1. Am I right? What is delta? Time required to stabilize both S0 and C1. But full adder one is not using S0 in this circuit. It is using only C1. Be clear about concept. So full adder one is using only C1. It is not using S0. What is delta? Time required to stabilize both sum and carry out, or S0 and C1. Delta is time required to stabilize both sum and carry out. But here in this full adder one, I'm not using S0. I'm using only C1. If I know carry circuit delay separately, TS and TC if it is provided, TS and TC if it is provided, why should I go with the optimistic analysis? Because in this TS may be greater than TC, TS may be less than TC, TS may be equal to TC. Understand correctly? What is it here? In this TS may be greater than TC, or TS may be less than TC, or TS may be equal to TC. Irrespective of all this, we are waiting for delta time. What is delta? Maximum of TS comma TC. For example, carry time is 2 nanoseconds, sometimes is 4 nanoseconds. For example, in this TS is 4 nanoseconds, TC is 2 nanoseconds. What is delta? 4 nanoseconds. What is delta? 4 nanoseconds. That means our analysis is saying that full adder one has to wait for 4 nanoseconds. In reality, it is not required. Even though C1 is changing, it has to wait for only 2 nanoseconds. So 4 nanosecond, 4 nanosecond, 4 nanosecond, 4 nanosecond. Then it becomes 16 nanoseconds. In that, pessimism is there. The pessimism must be eliminated. What do you mean by this? Full ladder one is not waiting for both S0 and C1. It is waiting for only C1. It is waiting for only C1. Be clear about this. Example I mentioned here. TS is 4 nanosecond. TC is 2 nanoseconds. What is delta? 4 nanoseconds. Now what you are saying that full adder one is waiting for 4 nanoseconds. Not required. It is not required. Why? Full adder one is waiting for only C1. That C1 will be ready in how much time? 2 nanoseconds only. That analysis we are going to do. What is that? Let us see. So full adder one is waiting for C1. Once C1 is getting, it started producing S0, S1 and C2. Again, full adder 2 is waiting for C2 stabilization only. Once C2 is ready, then it can start producing S2 and C3. Once C3 is ready, it can start producing. So that's what we need to understand. That's what we need to understand. What is that? Let us see. See, in this adder, whatever we have analyzed till now, in that we have a pessimism. The pessimism must be eliminated. In this, each full adder is waiting for carry from previous bit addition. Observe correctly. So in this, assume all the inputs are operated at 0 time. Which are the inputs? A0, A1, A2, A3, B0, B1, B2, B3, and C0. All these are operated at 0 time. And I know each full adder is taking that TC time to produce carry, TS time to produce sum. Shubham. क्या हुआ? Right. Shubham. Already I told you this, when you have multiple outputs, the time required to stabilize the output, or if a full adder, if I say, what is full adder delay? Time required to stabilize all the outputs, right? Some generation time, for example, some generation time is 4 nanosecond, carry generation time is 2 nanosecond. What is full adder delay? What is full adder delay? 4 nanoseconds. Why? Maximum of 4 nanoseconds, 2 nanoseconds. Already we discussed earlier also. A full adder is considered using 2 off-adders and so and so. One is generated in 4 nanoseconds, other one is generated in 4.5 nanoseconds. What is full adder delay? 4.5 nanoseconds. Maximum of TS comma TC. Shubham. If I keep on reading your messages, 200 people, I will be here. I did not see your message. When I see, I will respond. Right? So please wait. Question hour is there. We discuss. Keep on raising the hands, and please understand. One person is dealing with 200 students. Then listen, I will help you. Once you are having a doubt, right? Please note down that and note down the frame number. I'm there to help you. Please. So already I discussed. I am not using anything you have, or I'm not assuming that you have some concepts. Every point I've been discussing. Why we are saying that maximum of TS comma TC is if a circuit is having multiple outputs from the point inputs applied, what is the time required to stabilize all the outputs? That means maximum of output delays. That's what we are using. Already I have used, already I have given an example. Same thing I am applying here. Delta is maximum of TS comma TC. What is delta? Full adder delay. In that area analysis, we have a problem. What is it here is there is a pessimism. That pessimism must be eliminated because each full adder is waiting for carry from previous bit addition. It is not waiting for sum and carry from previous bit addition. The concept is each full adder is waiting for carry from previous bit addition. It is not waiting for carry plus sum from previous bit addition because carry only used in this. Am I using S0 in this? No, I'm using only C1. Once C1 is ready, it can start producing its outputs. That optimization we are doing now by knowing propagation delay of a full adder separately for sum, separately for carry. If it is mentioned how to calculate a propagation delay. Right? समझ में आ रहा है? I'm getting tired. Continuously shouting. Wait, 2 minutes, sir. I will talk. Yes, Shubham, that's what I'm going to analyze. Shubham, wait, let me do that. Otherwise, I'll make you as host. Please continue the class. I'm getting tired. Please wait. Let me do step by step. Right. Wait. Right. Now, full adder 0 is getting A0, B0, C0 at what time? 0 time. How much time it takes to produce C1? How much time? How much time? TC time. Just TC time. Because I know what is carry time now. When I know carry time in a full adder, so it is producing output carry in TC time. What about full adder 1? A1, B1 is ready at what time? 0 time. A1, B1 is ready at 0 time, but C1 is getting ready by TC time. That means full adder 1 is getting all the inputs at what time? TC time. To produce output carry, again it is taking TC time only because full adder is taking carry time to produce output carry from the point input stabilized. So if it is changing, it takes another TC time to produce C2 means it is a 2 TC. It is a 2 TC. Once again, full adder 1 is getting A1, B1 is ready at 0 time only. But when C1 is changing, the C1 is getting ready in how much time? TC time. So all the inputs of this full adder 1 will be ready at what time? TC time. Now, then onwards, if C2 is changing, it takes another TC time. So how much time is that? 2 TC. In 2 TC time, this full adder 2 inputs are ready. Why? A2, B2 is ready at 0 time. C2 is getting ready by 2 TC time. So full adder 2 inputs are ready at what time? 2 TC time. Now, full adder 2 output carry C3. If it is changing, it takes another TC time. Means at what time this is ready? 3 TC. It is a 3 TC. It is 3 TC. Once C3 is ready, full adder 3 is taking another TC time to produce C out. At what time this will be ready? 4 TC. Yes. Not completed. Listen. Full adder 3 is getting C3 at what time? 3 TC. Because of these C3 changes, if there are changes in some S3, how much time it takes? TS time. From the point, inputs ready. So A3, B3 ready at 0 time, but C3 is taking a 3 TC time. Then onwards, it is taking TS time means S3 will be ready by DTC plus TS. DTC plus TS. Any doubt in that? And what about this S2? From the point inputs ready, it takes TS time means 2 TC plus TS. What about S1? What about S1? TC plus TS. What about S0? TS time. Because its inputs are ready at 0 time, full adder takes TS time to produce some, it is TS time. Correct? So each and every output, what is the time required to stabilize, we have mentioned. Any doubt in this? Any doubt in this? Wait. Gopal Krishna Reddy. I do that. I haven't done that. Let me do that. See, what we are getting here, these are the delays of each and every output. What is the delay? What is the delay of this 4-bit adder now? Whichever is maximum in these two. Am I right? Maximum of 4TC, 3TC plus TS. Or I can write that 4TC as 3TC plus TC. Am I right? I hope you are understanding. I am writing 4TC as 3TC plus TC. In these two, if you are observing 3TC plus TC, 3TC plus TS. That means T4 bit is equals to what we can write? 3TC plus maximum of TS comma TC. Maximum of TS comma TC. Check it correctly. T4 bit is equals to 3TC plus maximum of TS comma TC. Because the difference between these two is TC and TS only. 3TC is common. The common I have written outside. Then which one will be maximum in these two? Whichever is maximum in TS and TC. So 3TC plus maximum of TS comma TC for 4 bit. For n bit, what is it? N minus 1 TC plus maximum of TS comma TC. So for this adder, Tn bit is equals to what is it? N minus 1 TC plus maximum of TS comma TC. Maximum of T. So what is maximum of TS comma TC? One full adder delay. What is N minus 1 TC time? What is 3 TC time here? Carry stabilization. That is 3 TC. So if it is n bit adder, n minus 1 TC is carry stabilization time or carry rippling time. Carry rippling from here to here, here to here, here to here. This n minus 1 TC time is a carry rippling time. So maximum part of this n bit adder is n minus 1 TC plus one of these will be added, but maximum part is n minus 1 TC. So in this analysis, the delay consisting of rippling carry time or parallel ripple carry adder. It is parallel adder only, but analysis is including rippling carry time. So parallel ripple carry adder. Parallel ripple carry adder. Parallel ripple carry adder. So it is parallel adder only, but the concept is a rippling carry concept. So it is a ripple carry adder. It is a ripple carry adder. Parallel ripple carry adder. So when can we use a ripple carry adder? In a full adder. In a full adder, if carry time separately, sometimes separately specified, then we use a ripple carry adder. Once again, and here both are using same properties. The only thing is one delay is specified for full adder, then we go with n delta. If two delays, that is sometimes separately, carry time separately, if it is specified, then we go with the ripple carry adder. These two are parallel adders only. These two are parallel adders only. Are you there? Right? So finally, what we have understood, rippling carry time is deciding propagation delay of n bit adder. Propagation delay of n bit adder. So this n minus 1 TC time are here the 3 TC time is nothing but carry rippled, carry rippled, carry rippled. So the C0 is ready at 0 time, but C1 is not ready, C2 is not ready, C3 is not ready. For these, it is taking 3 carry times in 4-bit adder. So n minus 1 TC time is for n bit adder. What is n minus 1 TC? Carry rippling time. So carry is getting rippled from one stage to another stage. So carry rippling time is n minus 1 TC. So analysis is a maximum part is n minus 1 TC. So rippling carry time is deciding propagation delay of this n bit adder. So it is named as a parallel ripple carry adder. It is parallel adder. Why? We are applying parallelly all the inputs and parallelly we are observing the outputs. But after how much time we need to check the result is a n minus 1 TC plus maximum of TS comma TC. When it is n bit adder, after applying inputs, after how much time we can check the result is a n minus 1 TC plus maximum of TS comma TC. To produce carry and 15 nanoseconds to produce sum. The propagation delay of 16-bit ripple carry adder is dash nanoseconds. Question. Yes. Sahil, in this slide, delta is maximum of TS comma TC. So, which one is more? We don't know. Delta is maximum of TS comma TC. Excellent. Huh? Very good. Very simple question. Yes, very good. T 16-bit is equals to what we can write 15 TC plus maximum of TS comma TC. Then 15 into TC is how much? 12 nanoseconds plus maximum of what we can say 15 nanoseconds comma 12 nanoseconds. Then 15 into 12 nanoseconds plus 15 nanoseconds. Finally, how much is that? 195 nanoseconds. Gopala Krishna Reddy. What happened? maximum frequency of 4-bit triple carry additions is dash. Excellent. Very good. Ramya, I'm asking frequency. How many 4-bit additions per second can be performed maximum? Sajjan Singh, check your answer. Maran Reddy, Dwarakanand Reddy. Don't use small m. I hope you have done correctly, but it becomes a milli. Right. So I need to perform 4-bit additions. How many 4-bit additions can be performed per second? That's what we need to calculate. So first, let me calculate. T 4-bit is equals to 3TC plus maximum of TS comma TC. Then 3 into 20 nanoseconds plus maximum of 40 nanoseconds comma 20 nanoseconds. How much is that? 60 nanoseconds plus 40 nanoseconds. It is 100 nanoseconds. That is one 4-bit addition can be performed in 100 nanoseconds. So how much time I need to wait for one 4-bit addition? 100 nanoseconds. Can I wait lesser than that? No, because it may be giving wrong result when you're applying input combinations which are taking worst case delay. So whatever we are calculating is 100 nanoseconds is worst case delay. But if I wait lesser than that, I don't know what input combinations I'm applying. When I'm applying worst case input combinations, it may not be giving correct result. If you are waiting lesser than 100 nanoseconds. Can I wait more than 100 nanoseconds? Not a problem. So, I can reach Delhi in 2 hours. Right? So, if someone is ready at 2 hours, he can pick me up. He comes after 2 hours, 10 minutes also, he can pick me up because I won't be there because I have arrived, I will be there only. So data is ready. Output data is ready in 100 nanoseconds. If you wait for 110 nanoseconds, there won't be any problem. The data will be stable because I'm not changing my inputs because I'm waiting for 110 nanoseconds means I'm not applying next inputs. So once outputs are ready in 100 nanoseconds, there won't be any problem. Right? So I can wait more than 100 nanoseconds. Or for example, someone has come to airport to pick me up in 1 hour 30 minutes itself, will I be there? No. No. So in worst case, it is taking 2 hours. I may be there, may not be there in 1 hour 30 minutes. So finally, what is it here? I cannot wait lesser than 100 nanoseconds. Some people have been doing that by using that maximum, instead of maximum of TS comma TC, minimum of TS comma TC. That is a wrong analysis. To minimize this, to maximize that frequency, people have been doing that. Instead of using that 3DC plus maximum of TS comma TC, people have been using a minimum of TS comma TC. Will be wrong analysis. So for 1 4-bit addition, compulsory we need to wait for 100 nanoseconds. Can I wait lesser than 100 nanoseconds? No. I can wait more than 100 nanoseconds. There won't be any problem. So this is the minimum time I need to provide for 1 4-bit addition. One slot is 100 nanoseconds. The slot can be more than 100 nanoseconds. There won't be any problem. I hope you are understanding. 1 4-bit addition slot is 100 nanoseconds. If I wait more than 100 nanoseconds, there won't be any problem. A slot. 1 4-bit addition slot, if I am fixing 100 nanoseconds, there won't be any problem. If you are waiting for more than that, not a problem. If you are waiting less than 100 nanoseconds, functionality may not be meeting. So, compulsory, I need to wait for 100 nanoseconds. That is the minimum slot for 1 4-bit addition. Because it has to produce the output in any conditions. Can I wait more than that? Not a problem. If you wait for 1 4-bit addition, if it is 200 nanoseconds, not a problem. In 100 nanoseconds, in worst case also, it is ready. If you are waiting for 200 nanoseconds, there won't be any problem because after applying inputs, outputs are produced, your inputs are not disturbed in 200 nanoseconds. Yes, if you are waiting for 200 nanoseconds, also not a problem. But you cannot wait lesser than 100 nanoseconds. The reason is a minimum time we need to wait for 1 4-bit addition. So F frequency is 1 by T4 bit equals to 1 by 100 nanoseconds. So it is a 10 power 7 per second, which is nothing but 10 megahertz. 10 megahertz. Bhaskar, why are you getting 0.01? Abhijit, check it. Yes, 10 megahertz. Neeraj Meshram. Wait. Why are you raising your hands? Did I say that now questions time? Right. Okay. For today, let me stop here. If you have any doubts, you can wait. Otherwise, you can leave the session. Just a minute. Let me save this. Ashish.
Good evening, sir.
Very good evening, Ashish. Tell me.
Sir, my doubt is from selective prime implicant, sir. In previous questions, as we have calculated the minimal expression for in some questions, sir, we take there were two possible minimal, sir.
Minimal expressions. Yes.
Yes, sir.
Yes.
So in one expression we were taking another term, and other we are taking other, sir. So
Yes.
is it is mean it does it
Yeah.
mean?
What you want to say? Let me complete that. You want to say that one you are considering, other one is redundant?
No, sir. I'm saying that are those two terms that are we can say interchangeable.
Yes.
So those are selective prime implicants, or there is only one selective prime implicant.
Both are selective prime implicants.
So we will count as two selective SPI.
Yes.
Okay.
If it cannot be a redundant,
Okay, sir. Okay.
if it cannot be a redundant, if it is not a essential, obviously it becomes a selective.
So both are selective SPIs.
Yes, both are.
Thank you, sir. Sir, one more doubt, sir.
Yes, yes.
So there is a question, sir. There is no diagram. I'm just reading it. So
Okay.
if you can help me with this, I will be thankful. A circuit which is working as NAND gate with positive level logic system
Yes.
will
Yes.
work as dash gate with negative level logic system.
Or gate.
So
I'll talk about that. With voltages, after getting into logic family, I can say that which one is considered as logic 1, logic 0. I'll talk. Negative
okay,
logic
sir.
and positive logic.
Okay, sir, one more doubt, sir.
Okay.
It's assertion region type, sir.
Please, can you message me or WhatsApp me such questions, sir? Because everyone is waiting, right? Whatever the discussions I had here, please ask me questions in this, please.
Okay,
Don't
sir.
mind, right? Please, you can send me in WhatsApp. I will reply.
Okay, sir. Thank you, sir.
We both should not waste others' time. Please understand in a positive way, right?
Okay, sir.
Ashish, fine?
Thank you, sir. Okay, sir. No
Please
problem.
send me in WhatsApp, I will reply.
Okay.
Okay. Ashish.
Yes, sir.
Ashish.
That's it, sir. That's it. Thank you, sir.
Yes, yes. Okay. Prudvi,
Hello, sir.
very good evening.
Hello, sir.
Good evening, Prudviraj.
Good evening, sir. Sir,
Yeah.
n-variable logic means three variables ఉన్నాయి సార్ ఏబిసి అని బూలియన్ ఆల్జీబ్రాలో.
Okay.
మాక్సిమం నెంబర్ ఆఫ్ ప్రైమ్ ఇంప్లికెంట్స్ ఎన్ని వస్తాయి అని చెప్పి ఫార్ములా అడిగాడు సార్ వాడు.
నేను క్వశ్చన్ చెప్తాను, నేను చెప్తాను. నాకు టైం ఇయ్యి, నేను చెప్తాను.
ఓకే సార్.
Right. I will discuss about maximum number of functions, maximum number of self-dual functions, maximum number of
ప్రైమ్ ఇంప్లికెంట్.
right. I will discuss. Question ఏంటంటే అక్కడ m ప్రైమ్ ఇంప్లికెంట్స్ ఉన్నాయి, రైట్? m-1 essential ప్రైమ్ ఇంప్లికెంట్స్ ఉన్నాయి. అప్పుడు ఎన్ని మినిమల్ ఎక్స్ప్రెషన్స్ అనేది క్వశ్చన్ అది.
అది కాదు సార్, అలా అడగలేదు సార్. ఎన్ వేరియబుల్స్ ఉన్నవి ఎన్ని మాక్సిమం ప్రైమ్ ఇంప్లికెంట్స్ రావచ్చు అని చెప్పేసి అడిగాడు సార్.
అది ఫంక్షన్ డిపెండ్ అయి ఉంటుంది, కరెక్ట్ గా చెప్పలేము ఇన్నే వస్తాయని.
ఆన్సర్ సార్ 2n పవర్ మైనస్ అని ఇచ్చాడు, -1 ఇచ్చాడు సార్. 2n
చెప్తున్నా కదా, ఆ కన్ఫర్మ్ గా చెప్పలేము కదా.
వాడు జనరల్ గా అడిగాడు సార్, ఫంక్షన్ కింద ఏం లేదు సార్. అందుకనే
అదే నేను చెప్తాను, ఇలాంటివి తర్వాత చెప్తాను, సరేనా?
ఓకే సార్, థ్యాంక్ యూ సార్.
యుగశ్రీ. Yugasri.
Good evening, sir.
Very good evening, ma.
Sir, 24F, sir, page.
F, okay. Yes, yes, ma'am.
Sir, in the first problem, we can combine the 2 or 4 or 8 to 16 bits now, sir.
Yes.
Sir, here also 1 x also we can combine, sir.
So horizontally you are saying?
Yes, sir.
Combine. Will it be there in the expression? Combine like this.
Okay.
This corner one is essential, compulsory we consider.
Yes, sir.
These two are remaining. To cover these two, if I consider this one, it is covering only one. It is missing again. To cover this again, we have to use.
How many combinations is possible? That much we have to combine.
Here, we don't need to worry about such things, in presence of don't cares.
Okay.
Directly group for minimal expression possibility. Not a problem.
Yes, sir. Sir,
Right.
next page in question, you gave one question, sir. Next page.
Next page. Okay.
Sir, A bar dot C bar is coming, sir.
Here it is POS, A equal to 0 is uncomplementary.
Okay.
We are in POS, max terms and don't case. 0 is uncomplimentary, 1 is complementary. In this, A equal to 0 is not changing. Because,
Yes, sir.
right, understood?
Yes, sir.
Understood or simply accepting?
Yes, sir. A is not changing, but
A
C
is
is
not
not
changing.
changing.
Yes.
But 0 is zero.
0 is uncomplimentary because we are in POS.
Yes, sir.
Yes, we are in POS. If it is min terms and don't case, would have been A bar, C bar. Right? Okay. Any more?
Sir, minimal expression will come means bar is not there.
Minimal expression?
In question, minimal expression is there means A bar will not consider, A is considered.
No. Why? It's not like that. When you are writing a term considering variable, for example, let me take one example. A, B, C. For example, it is like this, max terms. Grouping is like this. What we get? A equals to 1, B equal to 0 are not changing. What we write? A bar plus B, right? A equals to 1, B equal to 0 are not changing.
Yes, sir.
B is 0, uncomplimentary. A equals to 1, complementary. In this, A equal to 0 is not changing, so it is uncomplimentary. In this, C equal to 0 is not changing, uncomplimentary. I didn't get your doubt, please.
Okay.
Please clear with your question. I will help you. Have you understood now?
No, sir. By solving, we will take 0 means A bar, 1 means A we will take na, sir. That's why
That is with min terms.
Okay.
Everywhere we have done that, not only this one, right? Here, we are observing, here it is CD11. Then what is sum term we have written?
Yes, sir.
Already I mentioned, if A, B, C, 0, 1, 0, if function f is 0, maximum expression is what? A plus B bar plus C. Am I right?
Yes, sir.
0 is uncomplimentary, 1 is complementary. Don't forget the basics which I mentioned. Right? Same way, here also, where is that? Yes, here also, in this A equal to 0 means uncomplimentary. Here C equal to 0 means uncomplimentary. For example, if the same thing would have been here like this, then what would have been here? If this octave is max terms, then it would have been A bar because A equals to 1.
Okay. Oh.
You got it,
Yes, sir.
right? Understood? Clear? Are you there?
Yes, sir.
Understood? Have you understood?
Yes, sir.
Any doubt?
No, sir.
Thank you.
Thank you.
Ankur Kashyap.
Sir, I have some doubt from the classroom practice question.
What is it?
From classroom practice question.
Classroom practice questions of which one?
From logic gate and Boolean algebra, question number 3.
Question number 3. What was the question? Can you say?
How many min terms
Yeah,
excluding?
I will discuss. I will discuss in the class.
Okay.
If that is a question, I will discuss in the class. Express y bar z, right?
Okay. Yes, sir.
Yes.
So
I'll
I have
discuss.
one more doubt, sir, from KML.
Okay.
For an n variable Boolean
I
function.
will discuss. I will discuss. All
Okay,
such term questions I will discuss.
Okay, sir.
Right. I'll discuss those questions.
Okay, sir. Thank you, sir.
Right. Manisha.
Good evening, sir.
Very good evening, ma'am. Tell me.
Sir, I have a doubt in 44 frame, sir.
44. Okay.
Sir, here you mentioned the previous one, sir.
Here. Okay.
Yeah, here you mentioned that the carry only have a weight so that we won't consider the sum, the delay of sum.
So the case is, if I consider sum time is 4 nanosecond, carry time is 2 nanosecond. What is delta?
4 nanoseconds.
4 nanosecond. That means what you are saying that after applying A naught, B naught, C naught, it is waiting for 4 nanosecond. Do you accept that?
No, sir.
It is waiting for only 2 nanoseconds, right?
Yes, sir.
Because it requires only carry.
Yes, sir.
For carry and some generation, it requires 4 nanoseconds. But in this, only carry is used means for carry it is waiting for 2 nanoseconds.
Yes, sir.
That's what analysis. Carry time, then again carry time, again carry time. That's what we are using in ripple carrier.
Okay.
Right.
Okay, sir. Sir, I have a doubt. Doubt that like these full adders are there, na sir. Normally we use full adders means full adders or full subtractors as a binary addition and binary
Yes, binary.
2's complement addition, right, sir?
So
Then
that
why
is
we use subtractors?
2's complement
separate?
addition we won't do. Listen. 2's complement addition we